Guess what, Adam?
What, Martha?
We have finally made it. We get to learn about sample-based RL methods. And you know what that means, right?
Maybe?
We can learn solely from trial and error interaction. Only from experience. Our agents can learn how the world works on their own. This means we don't need a model of the world. All we need is data.
But we can still use the model, if we have it, by simulating experience from it. In fact, you'll see how many sample-based learning algorithms are based on value functions and ideas from dynamic programming. This includes one of the most fundamental algorithms in reinforced learning, called temporal difference learning.
We'll mirror the structure of Course 1. We first start with methods to learn value functions for prediction. Then you'll see how to learn action values for control. Finally, we'll talk about how to do planning with a learned model.
We will kick things off with Monte Carlo methods, and after that, we will discuss how TD methods can also be used for prediction and control. We will see how TD control methods like SARSA and Q-learning are connected to generalized policy iteration and Bellman operators. Along the way, we'll talk a lot about exploration, which is critical when learning from trial and error interaction.
You'll also be introduced to off-policy learning, which is essential when learning from experience. We'll finish this course with DYNA, an integrated architecture for planning, learning, and acting. We'll talk about some of the new issues that arise when planning with learned models that could be inaccurate.
Course 2 explores the foundations of online learning algorithms used throughout reinforced learning. We will continue in the tabular setting, for now, where we can learn a table of values assuming a finite MDP.
In Course 3, we'll extend our online algorithms to the function approximation setting. But for now, there are many issues to discuss and problems to solve, even in this simplified setting.
Let's continue our journey through the theory and practice of reinforced learning. So grab a drink and something to take notes with. Look at artificial intelligence. Here we come.
Hi, I'm Martha. I'm an assistant professor at the University of Alberta.
Hi, I'm Adam. I'm a research professor at the University of Alberta and a senior researcher at DeepMind.
Adam is well known for his work on predictive knowledge for reinforcement learning. Several research groups around the world are building on these ideas. I personally think it is some of the most important work in recent years and will only become more influential. He's also an impressive empiricist, a real master of designing experiments to cut to the key issues. He's constantly trying to improve scientific understanding in the RL community.
Martha's algorithm contributions to reinforcement learning are too many to list here. She has developed several new off-policy learning algorithms, new approaches to policy gradient, and dozens of impressive contributions to representation learning. She is truly one of the young rising stars in reinforcement learning. She also happens to be my most frequent co-author and my partner in life.
So how did you get into computer science?
Well, I grew up on the East Coast. In high school, I was really interested in the sciences, physics, chemistry, biology, but I couldn't really find a right fit. And so I kind of randomly took a course on computer science and programming, actually, in GW Basic. And it was really just a career-defining moment for me because I just remember the first time, implementing an if statement or a for loop, and it was just amazing to me that I could get a computer to execute a sequence of instructions for me. And so from there, there was no hope. I was always going to do computer science in college.
Okay, and then from there, why did you start working on reinforcement learning?
So for graduate studies, I moved out to Alberta, and I came out here to do parallel distributed computing. That's what I kind of focused on in my undergrad. So I had all my courses loaded up with, systems courses, and I had one more elective to fill. And so I was looking around for a course to take, and I did a very reasonable strategy. I looked at the pictures of the professors, and I picked the friendliest looking professor I could find. And yeah, that turned out to be Rich Sutton, and it was Introduction to Reinforcement Learning. And that course was amazing. It was really inspiring. It was my first introduction to artificial intelligence or machine learning of any kind. And so I remember one of the early assignments in that course, we were implementing SARSA to do a grid world. And again, it was another career-defining moment for me, just watching this agent learn to solve this maze. And all it got was this reward signal, -1 per step. And somehow it figured out this amazingly efficient path out of the maze. And again, it just amazed me, and I was hooked, and I was going to keep doing that for the rest of my life. So Martha, how did you end up doing research in machine learning and artificial intelligence?
Well, I actually started my undergrad in math. I've always thought functions and dynamical systems are beautiful. And then I just took a CS course for fun, and it really was very fun. So I just continued in both math and CS. And those two topics go really well together for AI and machine learning, actually. So and then I did some research in AI in the summertime and just continued from there. And I really just stayed in the field because over time I realized it was more than just about functions and math. It's really a community where you get to collaborate a lot and you get to make a career where you help people. So my day, I get to mentor a lot and I get to work in a big team working on hard problems, and it's really just very amazing to get to work on such interesting questions in a team. So there's probably some people who are taking this RL course because they want to do graduate studies in RL. So what's one of the most important things you learned in your graduate studies?
Well, maybe surprisingly enough, I learned a lesson that's useful across probably all the sciences and in fact just any form of research. And that's to really love coming to understand the details of things, to focus and do small problems and understand them really, really well. And that's something that I think is really applicable across a wide range of things, and it's something that I pass on to my students in my classes, and I really focus on teaching my graduate students that, and it's something that I hope to share to the people taking this specialization.
So what do you like about your job?
Well, I love doing research, but sometimes that can kind of grind you down a little bit. Like it's really long hours, the peer review process can be a little frustrating. And so in those times when you kind of step back and look at your research, it can seem kind of small and a little bit insignificant, and it's hard to see where that's going, how that's going to impact the world and make it a better place. And so in those times, you can always fall back and think about teaching and mentorship, right? Teaching is where you get to help people learn about things for the first time, to come to understand how your field works, and it's just so exciting. And you're also being part of the beginning of their careers, whether they end up in academia or industry or starting their own companies. It's just such an amazing experience to be part of that process. And throughout my week, the best day for me is always the days when my schedule is full of meetings with my students and I get to help them work on their problems and come to understand reinforcement learning better. So why do you think it's so important to work on reinforcement learning?
Well, I think the promise of RL is really big, but there are still a lot of open challenges. Machine learning has started being used much more widely, but RL has kind of only been used in a few areas. But at the same time, I think RL can have a really big impact. And I think within the next decade or so, we're going to see more control engineers actually using RL in their systems. We're really just going to see that it's a tool that can help in automated decision making, really within larger engineered systems. But I think for that to really happen, we need to make some advances in RL. We need to start thinking more about how we're going to have robust algorithms and how we're going to get people to be comfortable using these algorithms. So I think alongside adoption in industry, we're going to need to be thinking about how we can improve RL algorithms so that these two things can happen together. So how about you? Why do you think RL is good to work on?
Well, naturally, I think reinforced learning is just the exact right framework to study AI and to make progress towards solving AI. But RL is also really important to me because I'm very interested in developmental learning systems. So you can think about, humans, babies playing on the floor or young animals learning about the world. I want to learn about those systems and how they work. And if you think about those systems, they learn an enormous amount in such a tiny amount of time. Right? They learn how to crawl, they learn how their bodies work, they learn how to interact with their environment, manipulate objects, communicate with other agents in the world, and they're very competent learning systems, and they do that over like a couple weeks to a couple months, and it's just really astounding. And it feels like we have so much work to do to get close to those kind of systems. And so I really want to come to understand the algorithms and the representations that those systems might be using. And I think reinforcement learning is the right lens to look at those things and to come to understand those things. So applications always kind of drive interest and excitement in the field, and we've had a few of them in games and some industrial control problems. But what do you think is going to be the next big thing in reinforcement learning?
Well, at its heart, I think RL is just a general approach to automated decision making. It's a tool that's going to help us in a lot of our engineered systems. And so I think the place we're really going to see it take off is in industrial control. In industrial control, we have experts that are really looking for ways to improve how well their systems work. And so we're going to see it do things like reduce energy costs or save on other types of costs that we have in these industrial control systems. And in the hands of experts, we can really make these algorithms work well in the near future. So I really see it as a tool that's going to facilitate experts in their work rather than, say, doing something like replacing people or automating them away. The term Monte Carlo is often used more broadly for any estimation method that relies on repeated random sampling. In RL, Monte Carlo methods allow us to estimate values directly from experience, from sequences of states, actions, and rewards. Learning from experience is striking because the agent can accurately estimate a value function without prior knowledge of the environment's dynamics. By the end of this video, you will be able to understand how Monte Carlo methods can be used to estimate value functions from sampled interaction and identify problems that can be solved using Monte Carlo methods. Earlier, we talked about how reinforcement learning is connected to dynamic programming. To use a pure dynamic programming approach, the agent needs to know the environment's transition probabilities. In some problems, we simply don't know these probabilities. Imagine a meteorologist is trying to predict the weather. How the weather changes depends on a variety of environmental factors. We simply don't know the exact probability of weather patterns in the future. Calculating the transition probabilities used in dynamic programming is difficult even for reasonable tasks. Think about predicting the outcome of 12 rolls of dice. The sheer number and complexity of DP calculations makes them tedious and error-prone, both in terms of coding and numerical precision. Here's where Monte Carlo methods can help. Let's try to find the average sum of 12 dice rolls. Monte Carlo methods don't exhaustively sweep through all possible outcomes, like the one shown here. In fact, you don't need to know the probability of any outcomes to be able to use Monte Carlo methods. Instead, Monte Carlo methods estimate values by averaging over a large number of random samples. Let's roll 12 dice a few times and see the result. In this case, the average is 41.57, fairly close to the true average of 42. In reinforcement learning, we want to learn a value function. Value functions represent expected returns, so a Monte Carlo method for learning a value function would first observe multiple returns from the same state. Then, it could average those observed returns to estimate the expected return from that state. As the number of samples increases, the average tends to get closer and closer to the expected return. The more returns the agent observes from a state, the more likely it is that the sample average is close to the state value. These returns can only be observed at the end of an episode, so we will focus on Monte Carlo methods for episodic tasks. Monte Carlo methods in reinforcement learning look a bit like bandit methods. In bandits, the value of an arm is estimated using the average payoff sampled by pulling that arm. Monte Carlo methods consider policies instead of arms. The value of state S under a given policy is estimated using the average return sampled by following that policy from S to termination. Now let's look at an algorithm for estimating the state value function of a policy. The Monte Carlo algorithm has to keep track of multiple observed returns. Let's introduce a list of returns, one for each state. Each list holds the returns observed from state S. Then, we generate an episode by following our policy. For each state in the episode, we compute the return and store it in the list of returns. But how can we do that efficiently? Suppose the discount factor is 0.5, and imagine an episode ending at time step 5, where the reward sequence is 3, 4, 7, 1, and 2. Let's find each return G0 to G5, starting by writing down the equation for each return. Notice that each return is included in the equation for the previous time step's return. That means we can avoid duplicating computations by starting at G5 and working our way backwards. Let's do that now. The episode ends at t equal to 5, so G5 equals 0 by definition. G4 is equal to the reward at time 5 plus gamma times the return at 5, which adds to 2. G3 is equal to the reward at time 4 plus gamma times the return at time 4. The reward at time 4 is 1, and we just calculated that the return at time 4 is 2. Solving the equation, we can see that the return at time 3 is also 2. Continuing on, we can find the return at time 2 is 7 plus gamma times 2, which is 8. Finally, the first two returns, G1 and G0, are 8 and 7. By working backwards from the terminal time step, we can efficiently compute the returns for each state encountered during the episode. The first return is just the last reward, so we add the last reward to the list of returns for st-1. Then, we set the value of st-1 to be the average of returns st-1. On the previous time step t-2, we calculate the return as before, then add it to the list of returns for st-2. Finally, we update the value of st-2. If we continue this loop until the end, we'll have updated the values for all the states visited in the current episode. Then we can repeat the whole process over many episodes and eventually learn a good estimate for the value function. You might be wondering if we can avoid keeping all the sampled returns in a list. In fact, we can. We can incrementally update the sample average estimate using the formula here. Recall that we discussed using such incremental updates when estimating action values for bandits. We use the conceptually simpler sample average in this module to focus on the key ideas for Monte Carlo. After this module, we will switch to using the incremental update. In this video, we talked about how Monte Carlo methods learn directly from interaction. Notably, they don't need a model of the environment's dynamics. We also showed a Monte Carlo algorithm for learning state values and episodic problems. Imagine asking 1,000 people about their experience doing something and deciding to do that thing if most of their experiences turned out well. That's the essential flavor of Monte Carlo. Let's look at an example using Monte Carlo for prediction. By the end of this video, you will be able to use Monte Carlo prediction to estimate the value function for a given policy. Let's discuss the specifics of the Monte Carlo prediction algorithm using an example with the card game Blackjack. Blackjack is played with a standard deck of 52 cards. The objective is to collect cards so that their sum is as large as possible without exceeding 21. Face cards are counted as 10, while each ace can count as 11 or 1 based on the player's preference. The game begins with 2 cards dealt to both the player and the dealer. The player can see one of the dealer's cards, but the other is face down. If the player immediately has 21, they win, unless the dealer also has 21, in which case they draw. If the player does not have 21 immediately, they can request more cards, one at a time, or hit. If the sum of the player's cards ever exceeds 21, we say the player goes bust and loses. Otherwise, when the player decides to stop requesting cards, or sticks, it becomes the dealer's turn. The dealer only hits if the sum of their cards is less than 17. If the dealer goes bust, the player wins. Otherwise, the winner of the game is the player whose sum is closer to 21. We can formulate this problem as an undiscounted MDP where each game of blackjack corresponds to an episode. Rewards are given at the end of the game with -1 for a loss, 0 for a draw, and 1 for a win. The player has 2 actions, hit or stick. The player decides to hit or stick based on 3 variables: whether they have a usable ace, which is an ace that can count as 11 without their sum exceeding 21, the sum of their cards, and the card the dealer shows. There are 200 states in total. We assume that cards are dealt from the deck with replacement. This means that there's no point in keeping track of the cards that have been dealt and that the state respects the Markov property. Let's use Monte Carlo to learn the value function for the policy that sticks when the player's sum is 20 or 21. Suppose in the first state, the agent's card shows a total of 13 with no usable ace, and the dealer's visible card shows 10. Since the agent's policy is fixed, it hits and gets a 7, moving it to 20. The agent sticks because its sum is 20, and it's now the dealer's turn. The dealer draws a 9 and goes bust, losing the game and resulting in +1 reward for the agent. Now that the first episode is over, the agent can perform a Monte Carlo update and so start learning. The return from each state in an episode is +1 because the only non-zero reward is +1 at the end of the episode and the discount factor is 1. Now let's look at the states starting from the end of the episode and working backwards. In the last non-terminal state, the card sum was 20 with no usable ace and the dealer had a visible 10. Let's call this state A. We add +1 to the list of returns for state A and set the value of state A equal to the average of the list. Stepping back to the second last state, state B, the agent shows 13 with no usable ace and the dealer has a visible 10. Again, we add +1 to the list of returns, now for state B, and set the value of state B equal to the average of the list. We've now processed every state in the first episode and completed the Monte Carlo updates for that first episode. Now, what would happen if the agent played many games of blackjack? Let's look at the value function the agent learns after 10,000 episodes. We'll plot one value function for states with a usable ace and one for states without a usable ace. The three axes of the plot are the card the dealer is showing, the agent's sum, and the value of that state. The plot with usable aces is much more rough than the plot with no usable ace. That's because most blackjack games do not have a usable ace, so the usable ace values are estimated with far fewer samples. Both plots have a similar shape. Looking at the values going across the plot, it looks like the card the dealer is showing doesn't impact the value function very much. If we look at the agent's sum, however, the value function is much higher in states where the agent has a 20 or 21. Why are these values so much higher than when the agent has a sum of 19? The answer has to do with the policy the agent is following. The policy always hits on sums of 19 or lower, so the agent is likely to bust when the sum is 19. On the other hand, when the sum is 20 or 21, then the agent will stick and is likely to win. Now let's look at the value estimates after 500,000 episodes, and the estimates have nearly converged to the state values. Notice the plots are much smoother now. We see the same pattern as before, where the values are low unless the sum is 20 or 21. Now, what are some of the implications of Monte Carlo learning? First, Monte Carlo learns directly from experience, so there's no need to keep a large model of the environment. Monte Carlo methods can estimate the value of an individual state independently of the values of any other states. In dynamic programming, the value of each state depends on the values of other states, so this is a pretty big difference. Finally, the computation needed to update the value of each state along the way doesn't depend in any way on the size of the NDP. Rather, it depends on the length of the episode. In this video, we showed how to use Monte Carlo prediction to learn the value function of a policy, and talked about how Monte Carlo learning doesn't need to sweep over the whole MDP.
So far, we've talked about using Monte Carlo to learn state value functions for a fixed policy. This time we'll focus on learning action values. By the end of this video, you will be able to estimate action value functions using Monte Carlo and understand the importance of maintaining exploration in Monte Carlo algorithms. Learning action values is almost exactly the same process as learning state values. Recall that we learned the value of a state by averaging sample returns from that state. Conveniently, the same process works for action values. We collect returns following a policy from a state action pair and then take their average. But why do we care about learning action values at all? Action values are useful for learning a policy. They allow us to compare different actions in the same state. Then we can switch to a better action if one is available. This is only possible if we have an estimate of the values of the other actions, but this can be tricky. Let's consider learning the action value function for a deterministic policy. Imagine an action that is never selected by the policy. The agent will never observe returns corresponding to that action. We won't be able to form an accurate Monte Carlo estimate. the agent must try all the actions in each state in order to learn their values. This is the problem of maintaining exploration in reinforcement learning. Let's think about a real-world example. Imagine walking home along the road you usually take. Recently, a new road was built nearby. If we don't ever try the new way, then we couldn't know if it was actually better. One way to maintain exploration is called exploring starts. In exploring starts, we must guarantee that episodes start in every state action pair. Afterwards, the agent simply follows its policy. Consider the grid world on the screen. Let's see how exploring starts works with the policy shown in red. Exploring starts will randomly sample a state and action at the start of an episode, shown in blue. In this case, the blue action is not the same as the red one. After the initial action, the agent will follow the red policy until the episode ends. We must be able to set the start state in this way to evaluate a deterministic policy, like we can in this grid world. This may not always be possible. Other exploration strategies, like epsilon greedy, can be used to evaluate stochastic policies. We will talk more about that later. In this video, we describe the Monte Carlo algorithm for estimating action values and discuss the importance of maintaining exploration. Now that we have a generalized policy iteration algorithm for Monte Carlo control, let's use it in an example and see how it works. By the end of this video, you'll be able to apply Monte Carlo with exploring starts to solve an example MDP. Let's learn a policy. We will train our agent to play blackjack using Monte Carlo with exploring starts. Exploring starts requires that episodes begin with a random state and action. Luckily for us, our version of blackjack naturally starts in random states. Then, all we have to do is to randomly select the first action in each episode. That is, the agent ignores what it thinks is the best action in the first state and randomly chooses to hit or stick. The initial policy is hit when the agent's sum is less than 20, and to stick when the sum is 20 or 21. Let's step through a game and see what the algorithm would do. Suppose the agent's cards show a total of 13 with no usable ace, and the dealer's visible card is an 8. According to the randomly sampled first action, the agent hits. The agent gets a 7, moving the sum to 20. On the next step, the agent chooses the action according to its policy, so it sticks. Now it's the dealer's turn. The dealer draws a 9 and goes over 21, losing the game and resulting in a +1 reward for the agent. Great! Now let's look at the state action pairs we saw during the game, starting from the end of the episode and working backwards. In the last non-terminal state, the agent had a sum of 20, no usable ace, and the dealer had an 8. From that state, the agent chose to stick. The agent adds +1 to its list of returns corresponding to that state action pair. The estimated value for the action stick in this state is simply 1. Let's look at the value of the two actions in this state. The agent never tried the hit action, so its value is 0. The value of the stick action is 1. We just computed that. So the greedy action with respect to Q in this state is to stick. It has the highest estimated value. Let's move back in time one more step to the start state. The agent had 13 with no usable ace, and the dealer had an 8. The randomly chosen action was to hit. Again, the agent adds +1 to the list of returns following that state action pair. The average of the list forms the estimate of the action value. Finally, the policy is updated in this state to be greedy with respect to the action value estimates. In this state, we had never tried the stick action, and its value is 0. But the hit action resulted in a return of 1. So the greedy action is to hit, and the policy is updated to reflect this. We then repeat this process over many episodes. The action values and the policy will approach their optimal values. Let's look at the optimal policy that the agent found after we ran it for a really long time. Notice how the agent plays when it has a usable ace. For most dealer cards, the agent hits until it has a sum near 19. With the usable ace, The agent has a lot more flexibility in calculating the sum of its cards, so the policy is much more aggressive. Without a usable ace, the policy depends a lot more on the cards the dealer is showing. The agent sticks when its sum is 13 or greater, and the dealer has a low card, like a 2 or a 3. This is optimal, even though it seems like the chance of winning would be low in this situation. That's all for this time. In this video, we showed you how to apply Monte Carlo with exploring starts to an example MDP. We've hinted how the assumptions underlying exploring starts might limit the applicability of Monte Carlo control. In this video, we describe how to combine epsilon greedy exploration with Monte Carlo to learn near optimal policies. By the end of this video, you will understand why exploring starts can be problematic in real problems, and you will be able to describe an alternative exploration method for Monte Carlo control. Let's think about some situations where we cannot use exploring starts. This algorithm must be able to start from every possible state action pair. Otherwise, the agent may not explore enough and could converge to a suboptimal solution. In many problems, it can be difficult to randomly sample an initial state action pair. For example, how would you randomly sample the initial state action pair for a self-driving car? How could we ensure the agent can start in all possible states? We would need to put the car in many different configurations in the middle of a busy freeway. This would be dangerous and impractical. So how can we learn all the action values without exploring starts? Remember epsilon greedy exploration? We discussed this simple but effective method in the Bandit lectures. We can use it with Monte Carlo too. As a quick recap, epsilon greedy policies are stochastic policies. They usually take the greedy action, but occasionally take a random action. Epsilon greedy policies are a subset of a larger class of policies called epsilon soft policies. Epsilon soft policies take each action with probability at least epsilon over the number of actions. For example, both policies shown on the slide are valid epsilon soft policies. The uniform random policy is another notable epsilon soft policy. Epsilon soft policies force the agent to continually explore. That means we can drop the exploring starts requirement from the Monte Carlo control algorithm. An epsilon soft policy assigns non-zero probability to each action in every state. Because of this, epsilon soft agents continue to visit all state action pairs indefinitely. Epsilon soft policies are always stochastic. Deterministic policies specify a single action to take in each state. Stochastic policies instead specify the probability of taking action in each state. In epsilon soft policies, all actions have a probability of at least epsilon over the number of actions. They will eventually try all the actions. Let's look at an example of an epsilon greedy policy and a deterministic policy. Here we have a grid world with the arrows representing the deterministic policy. From the start state, the agent will follow the exact same trajectory through the grid world. The epsilon greedy policy has more arrows because every action has some small probability of being selected. Accordingly, the agent will probably follow a slightly different trajectory every episode. After enough episodes, it will have taken every action at least once in every state. This difference extends to the solutions that we find by exploring with epsilon soft policies.
That's fine.
If our policy always gives at least epsilon probability to each action, it's impossible to converge to a deterministic optimal policy. Exploring starts can be used to find the optimal policy. But epsilon soft policies can only be used to find the optimal epsilon soft policy. That is the policy with the highest value in each state out of all the epsilon soft policies. This policy performs worse than the optimal policy in general. However, it often performs reasonably well and allows us to get rid of exploring starts. Let's look at the pseudocode for Monte Carlo control with epsilon soft policies. It's easy to understand this algorithm by highlighting how it differs from exploring starts. There's one change to the initial conditions, one change to the policy evaluation step, and one change to the policy improvement step. The initial policy must be epsilon soft, such as the uniform random policy. The next change is how we use the policy to generate training data. Since the agent's policy is epsilon soft, we don't have to rely on exploring starts for exploration. Instead, the agent simply generates an episode following its epsilon soft policy. Finally, we improve the policy. The new policy is epsilon greedy with respect to the current action value estimates. You might think that this should be an epsilon soft policy rather than epsilon greedy. However, this makes sense because the optimal epsilon soft policy is an epsilon greedy policy. Even though this algorithm may not find the optimal policy, it does find the optimal epsilon soft policy. In future videos, we will discuss how to learn the optimal policy using a different method called Q-learning. In this video, we talked about the practicality of exploring starts and discussed Monte Carlo control with epsilon soft policies. That's it for this time. Go forth and explore safely.
We've discussed the exploration-exploitation trade-off. The key point is that the agent must occasionally take suboptimal exploratory actions, potentially receiving less reward. But maybe we do not need to make this trade-off at all. In this video, we'll discuss a new way of learning value functions called off-policy learning. By the end of this video, you will be able to understand how off-policy learning can help deal with the exploration problem. You'll also be able to produce examples of target policies and examples of behavior policies. Epsilon soft policies help with the continual exploration problem by having some small probability of exploring on each time step. The disadvantage of epsilon soft policies is that they are suboptimal for both acting and learning. Epsilon soft policies are neither optimal policies for obtaining reward, nor are they optimal for exploring to find the best actions. So far, throughout this course, we have implicitly been discussing on-policy learning, though we have not yet made a big deal of that name. In on-policy learning, the agent learns about the policy used to generate the data. What does it mean to learn about a policy? In policy evaluation, we simply mean learning the value function. In control, we mean learning the optimal policy. In off-policy learning, the agent learns about a policy from data generated by following a different policy. That is, the policy that we are learning is off the policy that we are using for action selection. For example, you could learn the optimal policy while following a totally random policy. We call the policy that the agent is learning the target policy because it is the target of the agent's learning. The target policy is usually denoted by pi. The value function that the agent is learning is based on the target policy. One example of a target policy is the optimal policy. We call the policy that the agent is using to select actions the behavior policy because it defines our agent's behavior. The behavior policy is usually denoted by B. The behavior policy is in charge of selecting actions for the agent. The behavior policy shown here is the uniform random policy. So why are we decoupling the behavior from the target policy? Because it provides another strategy for continual exploration. If our agent behaves according to the target policy, it might only experience a small number of states. If our agent can behave according to a policy that favors exploration, it can experience a much larger number of states. There are actually a few other useful applications of off-policy learning, such as learning from demonstration and parallel learning. But facilitating exploration is one of the main motivators. One key rule of off-policy learning is that the behavior policy must cover the target policy. In other words, if the target policy says the probability of selecting an action A, given state S, is greater than 0, then the behavior policy must say the probability of selecting that action in that state is greater than 0. There is a key mathematical reason for this that we will discuss in an upcoming video. But there's also an intuitive reason that we show here. Consider this state, where the behavior policy always goes up, but the target policy goes to the right. The agent cannot learn the correct action value for that state because it never observes samples of what would happen if it goes right. Maybe it gets a reward of +1 million. It would never know. It's worth noting that off-policy learning is a strict generalization of on-policy learning. On-policy is the specific case where the target policy is equal to the behavior policy. That's it for this video. The key points to take away from today are that off-policy learning is another way to obtain continual exploration. The policy that we are learning is called the target policy, and the policy that we are choosing actions from is the behavior policy. Today, we will discuss importance sampling. As we will see in later videos, importance sampling allows us to do off-policy learning, learning about one policy while following another. In this video, we will first describe how importance sampling works. By the end of this video, you will be able to use importance sampling to estimate the expected value of a target distribution using samples from a different distribution. Let's start by clearly stating the problem that importance sampling solves. We have some random variable x that is being sampled from a probability distribution B. We want to estimate the expected value of x, but with respect to the target distribution pi. Because x is drawn from B, we cannot simply use the sample average to compute the expectation under pi. The sample average would give us the expected value under B instead. Let's start with the definition of the expected value. We sum over all possible outcomes x multiplied by its probability according to pi. Next, we can multiply by b of x divided by b of x because this term is equal to 1. B of x is the probability of observed outcome x under b. Shifting around the numerator, we end up with a ratio between pi and b. This ratio is very important to us and is called the importance sampling ratio. We usually write the importance sampling ratio as rho of x. Now, let's go a step further. If we treat x times the importance sampling ratio as a new random variable times the probability of observing x, we can then rewrite this sum as an expectation under b. Notice that our expectation is now under b instead of being under pi. We know how to use importance sampling to correct the expectation, but how do we use it to estimate the expectation from data? It's actually very simple. We just need to compute a weighted sample average, with the importance sampling ratio as the weightings, as shown on the slide. Note that these samples xi are drawn from b, not pi. And that's it. We can now estimate the expected value of x under distribution pi by using the sample average with samples drawn from distribution B. Let's take a look at a small example of using importance sampling to estimate an expectation. We have two rather different distributions, B and pi. We'll draw samples according to B and try to estimate the expected value under pi. On the right, we'll keep track of our current estimate for the expected value under pi. For reference, we show the true expected value in the middle of the line. Let's draw a sample from B. We get x equals 1, which happens with probability 0.85. The probability of getting x equals 1 from pi would have been 0.3. To compute the sample average for pi, we need our importance sampling formula. Plugging in the observed values, we get an estimate of 0.35. Let's do it again. We draw a sample from B. This time x equals 3, which happens with probability 0.05. The probability we would have seen a 3 if we sampled from pi is 0.1. We'll add x to the buffer, then plug in the observed values into our formula. We take the previous estimate plus the new estimate and divide by 2 to get 3.18. And one last sample. We draw another 1 from B and add it to the buffer. We plug in the observed values to the importance sampling ratio formula and get 2.2. With samples just from B, we managed to get a pretty good estimate of the expectation under pi. That's it for this video. Today you learned how to use importance sampling to estimate expected values according to one distribution when data is sampled from another. See you next time. In recent videos, we've discussed off-policy learning. In this video, we'll see how to do off-policy prediction with Monte Carlo. By the end of this video, you will be able to understand how to use importance sampling to correct returns. And you will understand how to modify the Monte Carlo prediction algorithm for off-policy learning. Recall the goal of Monte Carlo estimation. We would like to estimate the value of each state by computing a sample average over returns starting from that state. We run into an issue, however, when we try to estimate the value under target policy pi using returns following a behavior policy b. If we simply average the returns we saw from state S under the behavior b, we will not get the right answer. We have to correct each return in the average. This is just what importance sampling is for. All we have to do is figure out the value of rho for each of the sampled returns. Rho here is the probability of the trajectory under pi divided by the probability of the trajectory under b. This rho corrects the distribution over entire trajectories, and so corrects the distribution over returns. Using this correction, we get back what we want, the expectation of the return under pi. To compute rho, we need to figure out how to compute the probability of a trajectory under a policy. Let's consider the probability distribution over trajectories. We read this probability as, given that the agent is in some state st, what is the probability that it takes action at, then ends up in state st plus 1? Then it takes action at plus 1 and ends up in st plus 2, and so on, until termination at time big T. All of the actions are sampled according to behavior b. Because of the Markov property, we can break this probability distribution into smaller chunks. The first chunk is the probability that the agent selects action at in state st times the probability that the environment transitions into state st plus 1. The second chunk gives the probability of the next time step of experience, and so on. We can rewrite this list of producted probabilities using the product notation. Now we've defined the probability of a trajectory under b. Remember where we are going. We would like to define rho using the probability of the trajectory under pi and the probability of the trajectory under b. Let's plug these probabilities into our definition of rho. As we saw in a previous video, we can take these probabilities and multiply them by the importance sampling ratio. The transition dynamics of the environment cancel out on each time step. This leaves us with only a product over the ratios between policies at each time step. Now let's get back to estimating v pi off policy. The agent observes many returns, each according to the behavior policy b. We can estimate v pi using these returns by correcting each return with rho. Now let's look at how we would implement this. First, recall the on-policy Monte Carlo prediction algorithm. There are two changes that will need to be made here. First, the episode will not be generated following pi, but will be generated following b. And second, the return will need to be corrected using the product of the importance sampling ratios. By making these changes, we end up with the off-policy Monte Carlo prediction algorithm. Notice the episode is now generated following the behavior policy. The return is corrected by a new term, w, which is the accumulated product of importance sampling ratios on each time step of the episode. We can compute rho from t to big T minus 1 incrementally. To see why, let's write out the product at each time step. Recall that the Monte Carlo algorithm loops over time steps backwards. So on the first step of the algorithm, w is set to rho on the last time step. On the next time step, w is the second last row times the last row, and so on. Each time step adds one additional term to the product and reuses all previous terms. We can compute this recursively without having to store all past values of rho. And that's it for this video. In this video, we use the importance sampling ratios to correct the returns generated by the behavior policy. And we modify the on-policy Monte Carlo prediction algorithm for off-policy learning.
Hi, I'm Emma Brunskill. I'm an assistant professor at Stanford University in the computer science department, where we think about reinforcement learning for high-stakes scenarios, particularly focusing on applications that we hope can benefit society. And what I'm excited to talk to you about today is batch reinforcement learning. But before we get started, I want to start with a brief motivation of saying of a tale of two hamburgers. Back in the 1980s, there's a fast food chain called A&W that is popular in the United States that was trying to compete with the Quarter Pounder of McDonald's, which is one of the most popular hamburgers. And so they thought they would introduce the Third Pounder. The taste tests were great, the beef was good, and they launched it, and the product failed. Unfortunately, even though the price of the Third Pounder was roughly similar to the price of the Quarter Pounder, people thought that they were getting less beef because 3 is less than 4. So I think this illustrates why mathematics education is extremely important. And when I heard about this story and when I started to think about reinforcement learning and its potential applications to society, education seemed like a really compelling example. And so together with my colleague Zoran Popovic and our graduate students, we were thinking about how we could better teach people fractions, hopefully in a way that was engaging, effective, and efficient. The game that you're seeing right now is called Refraction, and it's been played by hundreds of thousands of students. But one of the big challenges we had was to think about what is the sequence of activities students should do to keep them engaged and motivated and make sure they were learning. So for example, we can think of this as a decision policy, where based on the sequence of interactions with the game the student has so far, what is the next activity to give them in order to maximize some outcome we care about? This reward function could be something like persistence or the amount that they've learned. And in particular, in our case, these were optional learning environments. So we were really interested in trying to maximize student persistence. And so we started thinking about this about 5 years ago, and it made me really interested in the problem I'm going to tell you about briefly today. But I want to highlight here that I'm certainly not the first one to have thought about doing reinforcement learning for applications that could hopefully benefit society. Really since the very start of reinforcement learning, which we can trace back to sort of things like multi-armed bandits, as you heard about recently from the 1940s. There's been a parallel legacy of thinking about reinforcement learning to try to benefit humans, starting with things like teaching machines and then moving on to things like adaptive clinical trials. Now, I think this is both really exciting in terms of its societal impact, but it also introduces a lot of foundational questions for reinforcement learning. In particular, if we think about some of the extraordinary successes we see in reinforcement learning right now, they have tended to be in areas like robotics or game playing. And in those scenarios, we typically have access to a simulator where we can try things out, and even if our agent fails to learn for a long time, as long as it learns eventually, we're happy. In contrast, if we think about domains that involve interacting with people, we unfortunately do not yet have great simulators of how people learn or behave, which means that we have to rely on real data. But this is challenging because that real data involves interacting with real humans, which means that we need to be careful about the data we collect. And so one of the key questions that I think about, and together with my students in my lab, is how do we develop reinforcement learning techniques to try to minimize the amount of data an agent would need to learn? And what are the fundamental limits of how much information any agent would need to learn to make good decisions? And I think that if we can answer these questions, not only will we make foundational improvements to reinforcement learning, but also we'll be able to help more people. So I first just want to talk briefly about a quick refresher on MDP background. I think you're familiar with the notions of states and actions and next states, as well as dynamics models and rewards. And what I want to think about today is the counterfactual case. The idea that we're going to be getting data from the past, perhaps executed from a particular behavior policy, and we want to use that data in order to try to make better decisions going forward. Now, this is a challenging problem for a lot of reasons. In particular, it involves us thinking about what-if reasoning. Essentially, you can imagine that we have an agent that's made sequences of decisions in the past and got some outcomes. And maybe it's done this not just once, but a number of times. Now, one of the challenges is you could never know what your life would have been like if you weren't watching this video right now. That's a counterfactual, and you could never experience it. And so that's a key challenge when we try to think about using old data to try to make better, different decisions in the future. In particular, just like you saw in multi-armed bandits, we have censored data. We can't see what an alternative action would have resulted in, what the rewards are that we would have obtained. So this is a challenge that even comes up in multi-armed bandits, but when we think about using old data to do reinforcement learning, we actually have an additional challenge, which is the issue of generalization. So if you think about an agent making not just one decision, but a sequence of decisions, then the combinatorial possibilities of policies increases with the horizon. And so if we want to be able to generalize from our past data to think about what might happen under sequences of actions we've never experienced before, we're going to need some way to do generalization. Now, there are a number of us that are really excited about these problems of how to use old data to make better decisions in the future. And it's very closely related to things like causal reasoning and counterfactual reasoning. And these sorts of communities have a long history in other areas, like in statistics, epidemiology, and other aspects of computer science. But really, over the last few years, there's been a ton of excitement over trying to combine these ideas with machine learning methods and reinforcement learning in order to have more impact. So what I think that many of us would really love to be able to do is to do what's often called counterfactual or batch reinforcement learning, where we take old data, we learn a new policy from it, in a way that we know what that value will be when we deploy it in the future. And this is going to involve both doing policy evaluation, our ability to be able to evaluate how good an alternative policy would be, as well as policy optimization, where we take a max or an argmax over that set of possible policies we're considering. Now, I want to first talk briefly about the policy evaluation question, and I want to highlight that there's a huge literature on doing this, often called treatment effect estimation, from other communities. People in econometrics have thought about this extensively for things like how can you evaluate whether or not a treatment is better than a control decision. But again, when we think about sequences of decisions, we run into a challenge. This is a recent very nice paper from some of my colleagues of David Sontag and Pranali Doshi-Velez's lab. And what it illustrates is some of the challenges that come up when we start to use old data to try to make new decisions. In particular, imagine if you have sort of a set of patients who've been treated in a particular way, and now you want to think about a particular sequence of ways to treat them. So as we make decisions, as we do things like choose whether or not to ventilate a patient or choose whether or not to use sedation, the number of previous patients who had a particular sequence of interventions or a particular sequence of actions is going to be quite small. And so even if we start off with quite a large amount of data, say 100,000 patients, which is a reasonable number, we might only end up with, say, a few hundred patients who actually have received treatments that match the policy that we want to evaluate. And essentially, we can think of this as a challenge of covariate shift. That when we have different policies, those are generally going to be taking different actions, and those different actions are going to lead to different state distributions. And we really want to think about what would happen in terms of the resulting rewards under those differing state and action distributions that we expect to encounter. To try to tackle this problem of this distribution mismatch is importance sampling, which you recently heard about. So just as a refresher, in importance sampling, we can think about the value of a policy as being the probability of observing a particular trajectory. Right now I'm thinking about the finite horizon case. So we can think of the probability of generating a particular trajectory of states and actions times the reward of that particular trajectory, and then averaging that over all the trajectories we might receive. What importance sampling allows us to do, as you saw previously, is that we can use data that was generated from a different policy and reweigh it so that we can get a correct expectation. And one of the beautiful aspects of this is that we don't actually have to know the dynamics model of the world, because the dynamics model of the world is the same in the numerator and the denominator, so it cancels. And there's been a lot of exciting work in this area since this was first brought over to reinforcement learning, and it's a key tool for policy evaluation, because we can use it to take existing old data and use it to evaluate, under certain assumptions, what would be the value of an alternative policy. Now, I just want to highlight that there are some challenges with using importance sampling to do policy evaluation. Importance sampling provides us with an unbiased estimator, but it typically can be very high variance. In fact, in some of our previous work, we illustrated that the variance can scale sometimes exponentially with the horizon. And so that means if we don't have a lot of data or the horizon is long, that these estimators may be very poor approximators of how good our new policy might do in the future. An alternative is to use things like parametric models, which you heard about a little bit in terms of the MDP planning sections. So these models can have bias because sometimes the function approximators we're using or the model specification we've chosen is not correct. It doesn't match really how the world generates data. But they can have very low variance in return for some bias. And so one of the exciting innovations we've seen over the last few years is the idea of doubly robust estimators, an idea that comes from statistics but has been ported over to reinforcement learning and bandits over the last 10 years. And the idea is that we can combine between the best of these two worlds, of combining model-based estimators with importance sampling in order to get lower variance and lower bias. So this is a way for us to these are illustrations of the types of ways we can do policy evaluation. The thing that we would really like to do is to do policy optimization on top. And we have recent work that suggests that we can use these types of ideas, like importance sampling, in order to actually make better decisions going forward. In particular, here I show an illustration from Cartpole. The bottom line is showing us how good the current behavior policy is. And by using sort of advanced techniques, but building on importance sampling, we can actually do policy optimization and learn far better policies than we were using to actually collect the data. And I think this is very exciting in terms of the potential increases we could do by using these types of techniques. Now, this is just one step. I think that there's a huge amount of growth and open questions about how do we really solve this problem, particularly if we want formal guarantees on performance. In my lab, we've been doing a lot of work on the issues of policy evaluation, policy optimization, and trying to start deriving formal bounds so that we can be confident when we deploy these policies. And there's also a lot of really exciting work being done by my colleagues in these types of areas. So I think we have a long way to go, but before I close, I want to give us a reason for optimism. Which is if we go back to the example that I said at the beginning of looking at refraction, our goal there was to figure out if we could use old data from about 11,000 students to figure out if there's a better way to teach people and keep them more engaged. We used a method derived by importance sampling to get a policy that we thought would do about 30% better in terms of increasing persistence. We ran that study with another 2,000 students, and we found that indeed it increased by about 30 to 32%. And so I think this is really exciting as an illustration that sometimes we can predict the future accurately with these types of methods, and we really can make a difference. Thanks.
Well done! You've made it through the first week of lectures. This week was all about estimating value functions and finding optimal policies using only experience from the environment. We saw on-policy and off-policy Monte Carlo and revisited the exploration problem from bandits. Let's review the material so far. Monte Carlo algorithms are sample-based methods. They can be used when the model is unavailable or hard to write down. Monte Carlo algorithms estimate value functions by averaging over multiple observed returns. They wait for the full return before updating their values. Therefore, we use Monte Carlo only for episodic MDPs. We discussed how Monte Carlo can be used inside generalized policy iteration. This led to our first sample-based control algorithm, Monte Carlo with exploring starts. Monte Carlo algorithms don't do sweeps over the state action space like dynamic programming, so they need an exploration mechanism to ensure that they learn about every state action pair. We first considered exploring starts. Exploring starts requires that the first state and action are chosen randomly at the beginning of every episode. It is not always feasible or safe to use exploring starts. Just imagine trying to do exploring starts with an autonomous car. This realization motivated us to investigate additional exploration methods. We covered two other strategies for the exploration problem: learning on policy with epsilon soft policies and learning off policy. For the first strategy, the agent follows and learns about a stochastic policy. It usually takes the greedy action. A small fraction of the time, it takes a random action. This way, the value estimates for all state action pairs are guaranteed to continue to improve over time. This on-policy strategy forced us to learn a near-optimal policy instead of an optimal policy. But what if we want to learn an optimal policy but still maintain exploration? The answer lies with off-policy learning. We introduced some new definitions for off-policy learning, so let's review them. A behavior policy is the policy that the agent uses to select actions. A target policy is the policy that the agent learns about in its value function. By setting an appropriate exploratory behavior policy, the agent can learn about any deterministic target policy. One way to learn about one policy while following another is to use importance sampling. Importance sampling allows the agent to estimate the expected return under the target policy from experience sampled under the behavior policy. The ratio reweights the samples. It increases the importance of returns that were more likely to be seen under pi, and it decreases those that were unlikely. The sample average effectively contains the right proportion of each return so that in expectation, it is as if the returns had been sampled under pi. That's all for this module. Next, we'll talk about one of the most fundamental concepts in reinforcement learning, temporal difference learning. See you then! In the previous video, we introduced temporal difference learning. TD elegantly combines key ideas from dynamic programming and Monte Carlo methods. Like dynamic programming, TD methods bootstrap. Like Monte Carlo methods, TD can learn directly from experience. The combination is more powerful than the sum of its parts. By the end of this video, you will be able to understand the benefits of learning online with TD and identify key advantages of TD methods over dynamic programming and Monte Carlo. Let's consider the example of driving home from work. Each day, you predict how long it will take to get home. You base your predictions on the time, the day of the week, the weather, and other factors. Imagine that you have driven home many times before. You have a good estimate of how long it takes to get home from various situations you might encounter on the way. Let's look at these estimates for one trip home. One evening, as you leave the office, you predict it will take 30 minutes to get home. In about 5 minutes, you exit the parking lot and notice that it is raining. Traffic is slower in the rain, so you estimate that it will take 35 minutes then on to get home. 15 minutes later, you exit the highway earlier than you anticipated and estimate that it will now take you 15 minutes to get home. 30 minutes in your journey, you get stuck behind a slow truck and predict that it will take you an additional 10 minutes to get home. 10 minutes later, you enter the home street from where it usually takes 3 minutes to arrive home. Finally, 3 minutes later, you are home. So the numbers in the circles represent our predictions of remaining driving time. How can we improve these predictions? To understand how to update our predictions, we need to specify the reward. Let's use the amount of time taken. It took you 5 minutes to exit the parking lot. We can label this transition with a reward of 5. It took you another 15 minutes to exit the highway, and so on and so forth. You predicted that it would take you 30 minutes to get home, but it actually took you 43 minutes. Perhaps you can learn from this experience. Let's first look at a Monte Carlo method. In particular, we will use the constant alpha Monte Carlo method, with alpha equal to 1. In Monte Carlo methods, you update your estimates towards the return, which is only available at the end of the episode. We can only update the estimates for each of the states once we arrive home. We can start from when we leave the office. From the office, it took you a total of 43 minutes to get home. Therefore, the return at time 0 is 43. As alpha is 1, we move our estimate completely towards the actual return. From when you exit the parking lot, it took you 38 minutes to get home, and we update our estimate accordingly. We update the estimates for the remaining states in the same way. But is it really necessary to wait until the final outcome is known before learning can begin? Let's rewind the clock and look at how we would make updates with TD. From the office, it took you 5 minutes to exit the parking lot, from where you made a prediction of 35 minutes. From the exit state, you can update the estimate for office. Your current estimate from the office is 30 minutes. You get a reward of 5. The value of the next state is 35. So we update our estimate to 40 minutes. Let's consider the next state. Your current estimate is 35 minutes. It took you 15 minutes from the parking lot to exit the highway. The estimated time to get home for when you exit the highway is also 15 minutes. So we reduce the estimated time to go from when we exit the parking lot to 30 minutes. This makes sense because we exited the highway earlier than expected. We similarly update the estimates for the remaining states. As we make our way home, we can learn online without waiting to know the final outcome, unlike Monte Carlo. Let's summarize the advantages of using TD. Unlike dynamic programming, TD methods do not require a model of the environment. They can learn directly from experience. Unlike Monte Carlo, TD can update the values on every step. Bootstrapping allows us to update the estimates based on other estimates. TD asymptotically converges to the correct predictions. In addition, TD methods usually converge faster than Monte Carlo methods. We will see an example of this in the next video.
In the last few videos, we introduced TD and discussed its advantages over dynamic programming and Monte Carlo. In this video, we will dive deeper and compare TD and Monte Carlo in a carefully constructed scientific experiment. By the end of this video, you will be able to identify the empirical benefits of TD learning. Consider this simple MDP. We have 5 non-terminal states. In each state, we have 2 deterministic actions, left and right. Let's evaluate the uniform random policy. We want to estimate its value function. All episodes start in state C. Episodes terminate either on the left or on the right. The reward is 0 on all transitions, except +1 for terminating on the right. Let's set the discount factor to be 1. In this problem, the value has an intuitive meaning. The value of each state is the probability of terminating on the right when starting from each state. The value of the start state is 0.5. That means the probability of terminating from the center is a half. Randomly wandering from the center has a 50-50 chance of terminating on either side. That makes sense. Let's label the rest of the states with their values. Let's run an experiment right now. We have labeled the MDP with the true values at the top of the slide. The agent, our cute little robot, estimates the value function using TD. At the bottom, we have a Monte Carlo agent. Let's initialize the approximate value function for both agents to 0.5. Let's look at the performance of both agents during the first episode. Notice the TD agent only updated the value of state E. To understand this, consider the transition from state C to D. The TD error is equal to the reward on the transition plus the value of the next state, D, minus the value of state C. The reward is 0 because this is a non-terminal transition. The values of C and D are both 0.5. So the TD error is 0, and we make no change to the estimate for C. The same thing happens on every step except the transition into this terminal state from state E. In contrast, Monte Carlo updated the values of all the states the robot saw during the episode. Let's look at the next episode. Pay attention to how the values are updated during the episode. Eventually, the TD agent makes updates to the values on every step. In contrast, the Monte Carlo agent waited until the end of the episode before it made its updates. Let's look at a few more episodes. The value estimates of the TD agent seem to be moving towards the true values. This is taking too long. Let's jump ahead and evaluate the asymptotic performance. Let's plot the estimated values at several points during learning. The x-axis represents each state in the MDP. On the y-axis, we have the estimated value. Here are the true values. Let's also plot the initial value estimates. Recall, we initialized them to 0.5. The red curve shows the values learned after the first episode. By the end of the first episode, TD only updated the value of a single state, as we discussed. The estimates after 100 episodes are about as good as they're ever going to get. Remember, we're using a constant step size of 0.1. This means the values will fluctuate in response to the outcomes of the most recent episodes. If we use a smaller learning rate, or better yet, a decaying learning rate, we might get a better estimate. A natural next question is, does TD learn faster than Monte Carlo? Let's compare the performance of TD and Monte Carlo on our example problem. Here, the x-axis represents the number of episodes. The y-axis represents the root mean squared error between the value function and the learned estimates. The red learning curves represent the performance of Monte Carlo for several values of alpha. Each curve is averaged over 100 independent runs. For instance, this point represents the average error achieved after 50 episodes for the learning rate 0.01. Now let's look at TD's performance. We see that TD performed consistently better than Monte Carlo. Let's look a little more closely. Notice the error reduces faster with a learning rate of 0.15, but ultimately results in higher final error. With a smaller learning rate, TD learns more slowly, but achieves lower final error. In summary, we ran a careful experiment comparing TD and Monte Carlo, and the results suggest that TD converges faster to a lower final error in this problem. See you next time.
I thought we might talk about when we first decided that reinforcement learning was a thing.
Didn't we ever decide? No, I'd like to talk about those early days too, because there were some striking things about. So Rich was my first student, first graduate student. And I want to tell you something I don't think you know. So Harry Clough, who we wrote about it in the book in a number of places, but he created a contract at UMass to see whether his hypothesis about hedonistic neurons made any sense. And so I was hired as a postdoc, and Harry, according to Michael Arbiv, Michael was one of the PIs of the contract. It wasn't a grant, it was a contract. But Michael's memoirs, which have come out now, said that Harry required them to bring you aboard, or they wouldn't get the funding. You didn't know that. I didn't know that either until I read Michael's piece. The difference between, I don't think one reason we've worked together so well, I am by nature risk averse, and Rich is a risk-seeking person. I mean, he swims with sharks. That's the farthest thing. I mean, I think the risk aversion has.
Well, you're a contrarian. You don't want to go in the same direction as all the other people, which means one thing that means that you, as reinforcement has become so popular, you almost want to step aside of it. You are.
I go in orthogonal.
Yeah.
Mainly because I can't keep up with the literature. I have to find a field that is sparsely covered so that I can make a contribution. But now that I'm retired, I'm not going in any orthogonal direction at the moment. I'm amazed with what everybody's doing with reinforcement learning, and I'm thankful not to have to be in the thick of things. The industrial scale reinforcement learning, and it's great stuff, and it's just a flood of interesting papers, but I'm not keeping up.
Well, I want to talk about this topic, this contrarianness, this risk-seeking.
You're the risk seeker.
Well, but that you left your tenure track position to study a field that was unpopular.
To be a postdoc, I don't
To be a
recommend.
postdoc.
I don't recommend leaving a
And
tenure.
to study a field that was unpopular. So I know you don't see it as risk-seeking, but I think any other normal human being would. You wanted to pursue what you thought was important. Anyway, I don't want to make it about you, actually. I want to make it about the field. So the field was interested, well, it wasn't interested in learning, but I want to talk about reinforcement learning and supervised learning. And how in the 60s, in the first wave of neural networks and machine learning, it turned into supervised learning. The early guys in the 50s talked about things that were like reward, but then they ended up studying supervised learning.
So that's true.
And then that has happened over and over again through all the waves. There's always things coming up, but it's always a little bit of supervised learning versus reinforcement learning.
Well, I've seen things in the current literature by sophisticated people misunderstanding the distinction between error correction and trial and error.
And just
even
almost in the same way it's been misunderstood, throughout history.
Yeah, well.
Throughout 3 waves of neural networks since the 50s.
Yeah, that's true. We were charged with saying if Harry's ideas were worth studying. Had some, and so we went back and looked at everything, and we discovered real reinforcement learning among some people, but the field as a whole was focused on supervised learning, and those distinctions were not clear to people. That was a real revelation, and I remember my first round of talks back in those days was about that, saying, there's trial and error learning. It's not supervised learning. So that's true. It was a surprise. So I wrote this AI magazine article recently that kind of went through some of the surprises, and that was like number one. It was, wow, this is actually of course, that appealed to me because then maybe we could do something innovative that hadn't been done before, because most people hadn't studied it, except in engineering and statistical, stochastic control people and so on had been doing things like this, but it wasn't. The AI community didn't really latch on to that.
Well, the way I remember it, we looked through all the different fields. We couldn't find someone who'd studied learning to optimize a signal.
For what?
To optimize a signal.
Except for the learning automata people,
Yeah.
which nobody knew about.
Which was non-associative.
Yeah, pretty much.
I mean, there were a few works with bandits, but basically, the literature came up dry or with a very few things, and it was strange because this is an important kind of learning. It's just a strange fact that this thing is reinforcement learning. We now see we're having a second edition of a textbook on it, and we're having a course all about it, and it wasn't a thing. In 1980, it wasn't a topic. It was subsumed and swallowed up and obliterated. Couldn't be seen because of supervised learning.
Well, it also had suggestions of behaviorism.
Behaviorism was bad. Everyone knows behaviorism was bad.
One of the most unfashionable things around, and so reinforcement learning is behaviorism, and it includes elements of behaviorism, but not all of them. And we felt that people threw the baby out with the bathwater by rejecting common sense reinforcement learning principles. But even today, it's sort of called neo-behaviorism, which is irritating because, RL has models and value functions and all kinds of things that pure behaviorists would just not allow in their theories. It's not behaviors.
Well, it's all about what's going on in the algorithms inside the head. I guess pure behaviorism.
Well, we make up stuff that's in the
concepts.
head that you can't observe. So
Yeah.
behaviorists, at least pure behaviorists, wouldn't cotton to that.
But I learned a lot from the pure behaviorists. And I really think it's a shame that it was dissed, that it became unpopular. That's much of that's been lost. All that they have learned. On the other hand, it's sort of given me like a secret weapon, because I can understand what the behaviorists learned, and so many other people haven't bothered to learn. That's where temporal difference learning came from. And well, yeah.
And intrinsically motivated persistence, because throughout all of that, there were periods when there wasn't an extrinsic source of reward for the researchers. But it's sheer. Jeffrey, and I think us. And others. But some people would think it's foolish to keep studying the same thing. Alan Newell gave a talk. There's a video of it. And he characterized different kinds of researchers. And I forget all the names he gave them, but there were nomads. Nomadic research. So if something hot pops up, all the nomads move over to that area, study that for a while until something else pops up, and move over to that area. I think we've been the opposite of that. All sorts of things that popped up, but we've ignored them.
So that makes us the old fuddy-duddies.
Yeah.
And yeah, I don't know if it's contrarian or stubborn or.
Well, I got interested in intrinsic, what psychologists call intrinsic motivation, where you do something for its own sake rather than for an extrinsic reward of some kind. And I think, it's very powerful. I got interested in it because I thought and still think it's a good way to create sub-skills, options, or whatever you want to call them, from intrinsic. They might be useful in the future, but they might not. It's like basic research is intrinsically motivated. Whether there is utility, who knows? And it turns out there has been, it's incredible utility, but that was not the driving force, as opposed to, explicitly project-driven, which are important too, but the intrinsic, and I think animals go through an intrinsically motivated stage where they learn all kinds of skills, become competent at dealing with their worlds, and then when they have problems that they have to solve, they have an armament, they have sub-skills that they can bring to bear. And I think that's an important principle. And I think, I think I've been intrinsically motivated, Rich too, for these issues that now are, in the reinforcement learning set of ideas. To me, they're just interesting. And the fact that they work is a wonderful reward, but that was not the driving force, at least for me.
I think Andy, we've just had great success in reinforcement learning, and I just want to congratulate you and celebrate it with you and give you like a high five. Woo.
Congrats! You are now an expert on TD. In previous modules, we discussed dynamic programming and Monte Carlo. In this module, we took some of the best of both with TD learning. We started by borrowing an important concept from dynamic programming called bootstrapping. TD updates towards a bootstrap return. We can replace the return after time step t with the reward plus our estimate of the value in the next state. We say TD updates a guess from a guess. It bootstraps its value estimates towards the value of the next state. Then we discuss the tabular TD0 algorithm. The main takeaway here is that TD can update its value estimates on each step of the episode. It does not have to wait for the episode to complete. It just has to remember the previous state. How does TD compare to Monte Carlo and dynamic programming? Well, TD often converges faster than Monte Carlo. TD does not require a model, unlike dynamic programming. And TD is online and fully incremental, unlike either Monte Carlo or dynamic programming. We learned how TD updates its predictions as it receives new information. We demonstrated this by predicting how long it takes to get home from work. We used TD to continually refine our predicted arrival time at each stage of our drive home. Finally, we ran an experiment comparing TD and Monte Carlo on a random walk. On every transition, TD updates its value function to reflect the most recent information. In contrast, Monte Carlo only updates its value function at the end of each episode. In the long run, TD learned more quickly than Monte Carlo and achieved better final error. And that's it for today. In the coming weeks, we will build control algorithms using TD. I can't wait to see you then.
In previous videos, we talked about using generalized policy iteration to find an optimal policy. We've also talked about using TD to estimate value functions. But what would it look like if we used TD to do the policy evaluation step in generalized policy iteration? By the end of this video, you'll be able to explain how generalized policy iteration can be used with TD to find improved policies, as well as describe the SARSA control algorithm. Generalized policy iteration, or GPI, combines two parts: policy evaluation and policy improvement. The first algorithm we saw with this form was policy iteration. Policy iteration runs policy evaluation to convergence before greedifying the policy. Then, we saw GPI with Monte Carlo, which performs a cycle of policy evaluation and improvement every episode. To better remember GPI with Monte Carlo, imagine a mouse in a 4-state corridor with cheese at the end. The mouse starts out knowing nothing and follows a random policy. Eventually, the mouse will stumble into the cheese just by moving randomly. At that point, the mouse updates its action values. Then it improves its policy by greedifying with respect to its action values. As the process repeats, it will eventually learn the optimal policy. Notice that GPI with Monte Carlo does not perform a full policy evaluation step before improvement. Rather, it evaluates and improves after each episode. Going even further, we can improve the policy after just one policy evaluation step. We will do this with TD. To use TD within GPI, we need to learn an action value function. So, we'll need to look at slightly different version of TD than you've seen in the past. Instead of looking at transitions from state to state and learning the value of each state, let's look at transitions from state action pair to state action pair and learn the value of each pair. This algorithm is called SARSA prediction. Let's look at it in a bit more detail. The SARSA acronym describes the data used in the updates: state, action, reward, next state, and next action. SARSA makes predictions about the values of state-action pairs. The agent chooses an action in the initial state to create the first state-action pair. Next, it takes that action in the current state and observes the reward RT plus 1 and next state ST plus 1. In SARSA, the agent needs to know its next state-action pair before updating its value estimates. That means it has to commit to its next action before the update. Since our agent is learning action values for a specific policy, it uses that policy to sample the next action. Here's the full update equation. It actually looks quite similar to the TD update for state values, with state values V of S replaced by action values QSA. The algorithm we just described is for policy evaluation. It learns action values for a specific fixed policy. However, thanks to the GPI framework, we can turn it into a control algorithm. This time, we'll improve the policy every time step rather than after an episode or after convergence. This completes the description of SARSA, the GPI algorithm that uses TD for policy evaluation. In this video, we talked about how we can combine generalized policy iteration with TD learning to find improved policies. SARSA control is an example of GPI with TD learning.
Now that we've talked about what SARSA is, let's see what happens when we actually run it. By the end of this video, you will understand how the SARSA control algorithm operates in an example MDP. You will also gain experience analyzing the performance of a learning algorithm. Let's look at a windy grid world with a twist. The states form a grid with a single start state and a terminal state. The agent can move in the usual 4 directions. The agent receives a reward of -1 per step. This motivates the agent to escape as fast as possible. Since it's an episodic task, the discount factor gamma is 1. Here's where the twist comes in. A wind blows the agent upwards when moving out of certain states. The wind strength in each state depends on the column. For example, if the agent is in a column with wind strength 1 and takes the action left, it will move left and then up 1 cell. Moving into a boundary does nothing. Let's apply SARSA to this task. We will use epsilon greedy action selection. In this example, we'll use an epsilon of 0.1, alpha of 0.5, and initialize the values to 0. An epsilon of 0.1 means we take a random action 1 in every 10 steps. The initial values are optimistic, encouraging systematic exploration. This plot shows the total number of episodes completed after each time step. The results are averaged over 100 runs. Notice that the first few episodes take a couple thousand steps to complete. The curve gradually gets steeper, indicating that episodes are completed more quickly. Around 7,000 steps, the greedy policy stops improving. Notice the episode completion rate stops increasing. This means the agent's policy hovers around the optimal policy and won't be exactly optimal because of exploration. Notice that Monte Carlo methods would not be a great fit here. This is because many policies do not lead to termination. Monte Carlo methods only learn when an episode terminates. So a deterministic policy might get trapped and never learn a good policy in this grid world. For example, if the policy took the left action in the start state, it would never terminate. SARSA avoids this trap because it would learn such policies are bad during the episode, so it would switch to another policy and not get stuck. In this video, we showed an example of the SARSA control algorithm in an MDP. We also analyzed SARSA's performance to better understand its learning process.
Several recent applications of reinforcement learning, learning to play Atari games, control traffic signals, or even automatically configuring web systems, have been built on a single algorithm. This algorithm is called Q-learning. By the end of this video, you will be able to describe the Q-learning algorithm and explain the relationship between Q-learning and the Bellman optimality equations. Q-learning was developed in 1989 and is one of the first major online reinforcement learning algorithms. Let's take a look at the pseudocode. We've seen this format before. The agent chooses an action in a state, takes the action, and observes the next state and reward. Then the agent does an update, and the cycle repeats. With so many familiar elements, what's new about Q-learning? Well, the new element in Q-learning is the action value update. Here, the target is the reward, RT plus 1, plus gamma times the maximum action value in the following state. This differs from SARSA, which uses the value of the next state action pair in its target. Why does Q-learning use a max instead of the next state action pair? This connection goes way back to the dynamic programming material. If you look at the update equation for SARSA, it's suspiciously similar to the Bellman equation for action values. In fact, SARSA is a sample-based algorithm to solve the Bellman equation for action values. Q-learning also solves the Bellman equation using samples from the environment, but instead of using the standard Bellman equation, Q-learning uses the Bellman optimality equation for action values. The optimality equations enable Q-learning to directly learn Q star instead of switching between policy improvement and policy evaluation steps. Even though SARSA and Q-learning are both based on Bellman equations, they're based on very different Bellman equations. SARSA is a sample-based version of policy iteration, which uses Bellman equations for action values that each depend on a fixed policy. Q-learning is a sample-based version of value iteration, which iteratively applies the Bellman optimality equation. Applying the Bellman optimality equation strictly improves the value function, unless it is already optimal. So value iteration continually improves its value function estimate, which eventually converges to the optimal solution. For the same reason, Q-learning also converges to the optimal value function, as long as the agent continues to explore and samples all areas of the state action space. Let's review what we learned today. In this video, we introduced the Q-learning algorithm and described its connection to the Bellman optimality equations.
We just introduced you to Q-learning. You might not have a great intuition for why it works well. In this video, we'll demonstrate how to use Q-learning on the windy grid world and discuss the results. By the end of this video, you will gain insight into how Q-learning performs in an example NDP. You will also gain insight into the differences between Q-learning and SARSA. Let's go back to the windy grid world. It's an undiscounted grid world with wind that blows the agent upwards as it moves through the windy states. The wind strength is shown under each column of the grid. The agent can move in 4 directions and receives a reward of -1 on each step. For comparison, here is the performance of SARSA with an epsilon of 0.1 and an alpha of 0.5. Like before, this plot shows the number of episodes completed on the y-axis and the number of time steps on the x-axis. Recall SARSA learned slowly for the first couple episodes. Then it improved exponentially before plateauing. Let's use Q-learning with the same parameter settings. Before showing the results, let's think about what's going to happen. Perhaps SARSA's policy will perform better because its value function takes into account its epsilon greedy behavior. Maybe Q-learning will learn faster because it directly learns the optimal policy's value function. What do you think will happen? Here are the results. In the beginning, the two algorithms learn at a similar pace. Towards the end, Q-learning seems to learn a better final policy. Why is Q-learning doing so much better here? Without conducting more targeted experiments, we cannot know for sure. Perhaps the update target of Q-learning is more stable. Q-learning takes the max over next action values, so it only changes when the agent learns that one action is better than another. In contrast, SARSA uses the estimate of the next action value in its target. This changes every time the agent takes an exploratory action. Perhaps you could design an experiment to get to the bottom of this. For now, let's move on. How can we make SARSA perform better? A step size parameter value of 0.5 might be a bit high for this experiment. These large updates might be causing SARSA trouble when the agent takes exploratory actions. SARSA's final policy certainly isn't optimal. Let's run the experiment a bit longer, and this time with alpha equal 0.1. We expect SARSA to learn more slowly with a smaller alpha, but find a better policy. Let's see what happens. Prediction confirmed. SARSA learns the same final policy as Q-learning, but more slowly. We know both algorithms have converged to the same policy because the slopes of the lines are equal. Equal slopes mean that both agents are completing episodes at the same rate. This experiment also highlights the impact of parameter choices in reinforcement learning. Alpha, epsilon, the initial values, and the length of the experiment can all influence the final result. In this video, we evaluated Q-learning in the windy grid world and gained insight into the differences between Q-learning and SARSA on this simple MDP.
Q-learning is an off-policy algorithm, but so far we've only seen off-policy algorithms that use importance sampling. How can Q-learning be off-policy without using importance sampling? Let's dive in and find out. By the end of this video, you will understand how Q-learning can be off-policy without using importance sampling, and be able to describe how learning on policy or off policy might affect performance in control. Recall that an agent estimates its value function according to expected returns under their target policy. They actually behave according to their behavior policy. When the target policy and behavior policy are the same, the agent is learning on policy. Otherwise, the agent is learning off policy. SARSA is an on-policy algorithm. In SARSA, the agent bootstraps off of the value of the action it's going to take next, which is sampled from its behavior policy. Q-learning instead bootstraps off of the largest action value in its next state. This is like sampling an action under an estimate of the optimal policy, rather than the behavior policy. Since Q-learning learns about the best action it could possibly take, rather than the actions it actually takes, it is learning off policy. Whenever you see a reinforced learning algorithm, a natural question to ask is, what are the target and behavior policies? Q-learning's target policy is always greedy with respect to its current values. However, its behavior policy can be anything that continues to visit all state action pairs during learning. One possible policy is epsilon greedy. The difference here between the target and behavior policies confirms that Q-learning is off policy. But if Q-learning learns off policy, why don't we see any importance sampling ratios? It is because the agent is estimating action values with a known policy. It does not need importance sampling ratios to correct for the difference in action selection. The action value function represents the returns following each action in a given state. The agent's target policy represents the probability of taking each action in a given state. Putting these two elements together, the agent can calculate the expected return under its target policy from any given state, in particular the next state st plus 1. Q-learning uses exactly this technique to learn off policy. Since the agent's target policy is greedy with respect to its action values, all non-maximal actions have probability 0. As a result, the expected return from that state is equal to a maximal action value from that state. Earlier, we talked about how Q-learning doesn't iterate between policy evaluation and policy improvement, but rather learns the optimal values directly. Directly learning the optimal value function in policy sounds great, but there are some subtleties that make it less desirable in specific situations. Let's look at this cliff walking example to understand some of those subtleties. The cliff walking environment is an undiscounted episodic grid world with a cliff on the bottom edge. On most steps, the agent receives a reward of -1. Falling off the cliff, however, sends the agent back to the start and gives a reward of -100. We compare Q-learning and SARSA in this environment with an epsilon of 0.1. Here's the average performance of Q-learning. Since Q-learning learns the optimal value function, it quickly learns that an optimal policy travels right alongside the cliff. However, since its actions are epsilon greedy, traveling alongside the cliff occasionally results in falling off of the cliff. SARSA learns about its current policy, taking into account the effect of epsilon greedy action selection. Accounting for occasional exploratory actions, it learns to take the longer but more reliable path that usually avoids randomly falling into the cliff. Because of its safer path, SARSA is able to reach the goal more reliably. In this video, we showed that Q-learning is off policy without using importance sampling, and that learning on policy or off policy may perform differently in control depending on the task. We just discussed two TD control methods, SARSA and Q-learning. In this lesson, we'll talk about another TD control method called expected SARSA. By the end of this video, you will be able to explain the expected SARSA algorithm. Recall the Bellman equation for action values. Here you can see the expectation over values of possible next state action pairs. Breaking this expectation apart, we see a sum over possible next states as well as possible next actions. SARSA estimates this expectation by sampling the next state from the environment and the next action from its policy. But the agent already knows its policy, so why should it have to sample its next action? Instead, it should just compute the expectation directly. In this case, we can take a weighted sum of the values of all possible next actions. The weights are the probability of taking each action under the agent's policy. Explicitly computing the expectation over next actions is the main idea behind the expected SARSA algorithm. Now let's look at the expected SARSA's learning update. Since expected SARSA is still based on the Bellman equation for action values, it uses the familiar form of learning update. The algorithm is nearly identical to SARSA, except the TD error uses the expected estimate of the next action value instead of a sample of the next action value. That means that on every time step, the agent has to average the next state's action values according to how likely they are under the policy. For example, with the following values in policy, expected SARSA would use a value of 1.4 for its estimate of the expected next action value. However, there is a huge upside to calculating the expectation explicitly. Expected SARSA has a more stable update target than SARSA. Let's look at an example to make this more clear. In this example, the immediate reward is deterministically 1. Both SARSA and expected SARSA start out with the true action values for the next state. Even in this idealized case, the next action sampling that SARSA does can cause it to update its values in the wrong direction. It relies on the fact that in expectation, across multiple updates, the direction is correct. By contrast, expected SARSA's update targets are exactly correct and do not change the estimated values away from the true values. In general, expected SARSA's update targets are much lower variance than SARSA's. The lower variance comes with a downside, though. Computing the average over next actions becomes more expensive as the number of actions increases. When there are many actions, computing the average might take a long time, especially since the average has to be computed every time step. In this video, we showed that the expected SARSA algorithm explicitly computes the expectation under its policy, which is more expensive than sampling but has lower variance.
We've introduced the expected SARSA control algorithm. Now it's time to see it in action. By the end of this video, you'll be able to describe expected SARSA's behavior in an example MDP, and empirically compare expected SARSA and SARSA. We will use the cliff walk environment again, so we can talk about SARSA, Q-learning, and expected SARSA all at once. Let's recap. This environment is an undiscounted, episodic grid world with a cliff on the bottom edge. Moving into the cliff moves the agent back to the start with a reward of -100. Otherwise, the reward is -1 on each time step. SARSA performed better than Q-learning on this domain because SARSA's policy accounted for its own exploration. Today, we'll compare expected SARSA to SARSA with an epsilon of 0.1. This plot was created by testing each agent with different values of the step size parameter alpha. We did 100 episodes and averaged everything over 50,000 independent runs. The y-axis shows the average return per episode, and the x-axis shows the step size values. SARSA's performance increases with larger step size values, but only up to a point. The best alpha value for SARSA here was 0.9. Expected SARSA outperforms SARSA for almost all values of alpha. Expected SARSA is able to use larger alpha values more effectively. This is because it explicitly averages over the randomness due to its own policy. This environment is deterministic, so there are no other sources of randomness to account for. This means expected SARSA's updates are deterministic for a given state and action. SARSA's updates, on the other hand, can vary significantly depending on the next action. Now let's look at the average return per episode after 100,000 episodes. At this point, each algorithm has learned everything it's going to learn. Expected SARSA's long-term behavior is unaffected by alpha. Its updates are deterministic in this example. Therefore, the step size only determines how quickly the estimates approach their target values. SARSA behaves quite differently here. It even fails to converge for larger values of alpha. As alpha decreases, SARSA's long-run performance approaches expected SARSA's. In this video, we've seen that expected SARSA was able to quickly learn a good policy in the cliff world, and that expected SARSA is more robust than SARSA to large step sizes.
Up until now, we've seen 3 TD algorithms for control: SARSA, Q-learning, and expected SARSA. 2 of those algorithms, SARSA and expected SARSA, both approximate the same Bellman equation. Today, let's look at how expected SARSA is related to Q-learning. By the end of this video, you will understand how expected SARSA can do off-policy learning without using importance sampling, and explain how expected SARSA generalizes Q-learning. Let's start with the on-policy case, where the behavior policy and the target policy are equal. Consider the expected SARSA update. The next action is sampled from pi in this case. However, notice that the expectation over actions is computed independently of the action actually selected in the next state. In fact, pi need not be equal to the behavior policy. This means that expected SARSA, like Q-learning, can be used to learn off policy without importance sampling. Now, what happens if the target policy is greedy with respect to its action value estimates? We can see that only the highest value action is considered in the expectation. This is equivalent to computing the maximum over actions in the next state, just like in Q-learning. In other words, Q-learning is a special case of expected SARSA. In this video, we showed that expected SARSA and Q-learning both use the expectation over their target policies in their update targets. This allows them to learn off policy without importance sampling. Expected SARSA with a target policy that's greedy with respect to its action values is exactly Q-learning.
This week we learned how to use TD methods for control. In this video, we'll recap everything we covered this week. The TD control algorithms are based on Bellman equations. We learned about 3 of them. SARSA uses a sample-based version of the Bellman equation. It learns QPi. Q-learning uses the Bellman optimality equation. It learns Q star. Expected SARSA uses the same Bellman equation as SARSA, but samples it differently. It takes an expectation over the next action values. What's the story with on-policy and off-policy learning? SARSA is an on-policy algorithm that learns the action values for the policy it's currently following. Q-learning is an off-policy algorithm that learns the optimal action values. And expected SARSA is both an on-policy and an off-policy algorithm that can learn the action values for any policy. SARSA can do better than Q-learning when performance is measured online. This is because on-policy control methods account for their own exploration. In the cliff world, we saw that Q-learning frequently fell off the cliff because of its exploratory actions. SARSA learned the longer but safer path that rarely fell off the cliff. This resulted in higher reward. We then studied an improvement over SARSA called expected SARSA. In the cliff world, expected SARSA outperforms SARSA for all the step size parameter values we tested. This is because expected SARSA mitigates the variance due to its own policy. Expected SARSA, like the name suggests, takes the expectation over the next action. That's all for this module. Next, we'll learn how to combine planning, learning, and acting. See you then.
Sometimes we make decisions without thinking too much about them, such as deciding how to drive to work. Other times, we sit and imagine many possible scenarios based on our understanding of the world. We can use these imagined outcomes to decide what to do or what not to do. For example, if we carry a fragile object with one hand, we can imagine scenarios where it falls and breaks, and we can make choices accordingly. We've seen sample-based methods like TD, which learn only from sampled experience. We've also seen methods like dynamic programming, or DP, which plan by using complete information about how things work, without having to make decisions. It would be even better if we could obtain an intermediate method that can leverage the best of both extremes. This week, we will do just that and unify these strategies with the DYNA architecture. In this video, we will talk about models. By the end of the video, you will be able to describe a model and how it can be used, classify models as distribution models or sample models, and identify when to use a distribution model or sample model. Models are used to store knowledge about the dynamics. When imagining different scenarios to aid decision-making, this is rooted in our knowledge about how the world works. From a particular state in action, the model should produce a possible next state and reward. This allows us to see an outcome of an action without having to actually take it. A model allows for planning. Planning refers to the process of using a model to improve a policy. One way to plan with a model is to simulate experience and perform value function updates as if those experiences happened. By improving the value estimates, we can make more informed decisions. Simulating experience improves sample efficiency. The addition of simulated experience means the agent needs fewer interactions with the world to come up with the same policy. Now let's talk about the different types of models that may be useful to us. One is a sample model, which produces an actual outcome drawn from some underlying probabilities. For example, a sample model for flipping a coin can generate a random sequence of heads and tails. Another type of model is a distribution model, which completely specifies the likelihood or probability of every outcome. In the coin flipping example, it would say that heads could occur 50% of the time and that tails could occur 50% of the time. It could also produce the odds of any sequence of heads and tails using this information. Sample models can be computationally inexpensive because random outcomes can be produced according to a set of rules. For example, to flip 5 coins, a sample model can randomly pick 0 or 1 independently 5 times. It only needs to produce a single outcome for each flip. As an example of a sample model in practice, in 2017, the company Cloudflare used random patterns sampled from a wall of lava lamps to encrypt 10% of global internet traffic. The samples are random configurations of the lava lamp wall at a given point in time, with the procedure of rules to generate those samples defined by the dynamics of the lava lamps. Distribution models contain more information, but can be difficult to specify and can become very large. Let's go back to the example for flipping 5 coins. A distribution model would enumerate every possible sequence of heads and tails you could get across the 5 coins and assign a probability to each sequence. For this simple problem, that would consist of fully describing 32 possible outcomes. Distribution models can be used as sample models by drawing outcomes according to explicit probabilities of each outcome, but they contain more information than might be strictly needed just to obtain samples. In this video, we talked about how models can be used to improve a policy through a process called planning. We discussed 2 different types of models, sample models and distribution models. Next time, we'll go into more depth on the differences between these models. Models represent knowledge of how the world works. We've talked about 2 types of models, sample models and distribution models. In this video, we focus on a concrete example to illustrate the key differences between sample models and distribution models. By the end of this video, you will be able to describe the advantages and disadvantages of sample models and distribution models, and you will also be able to explain why sample models can be represented more compactly than distribution models. Let's consider the problem of rolling 12 dice. This can be done easily with a single die and enough patience. Rolling a single die 12 times is an example of a sample model. Programmatically, one would generate a random number from 1 to 6 12 times. This is very compact and does not consider joint probabilities. Modeling the complete joint distribution of rolling 12 dice is much more work. We must consider every possible outcome of 12 dice and assign a probability to each outcome. With 1 die, we have 6 outcomes. With 2 dice, we have 36 outcomes. 3 has 216. 4 has 1,296. And by the time you get to 12 dice, we have over 2 billion possible outcomes to consider. But it can be useful that a distribution model produces the exact probability of an outcome. For example, we can compute the expected outcome directly or quantify the variability in outcomes. Let's summarize the benefits of each type of model. Sample models require less memory. Distribution models, on the other hand, can be used to compute the exact expected outcome by summing over all outcomes weighted by their probabilities. Note that sample models can only approximate this expected outcome by averaging many samples together. Knowing the exact probabilities also has the flexibility of assessing risk. For example, when a doctor is prescribing medicine, they would consider many possible side effects and how likely they are to occur. In this video, we described how sample models can be more compact than distribution models, and how the explicit probabilities in distribution models can be useful in some situations, such as for computing expectations. Now that we know what models are, we can discuss how we might use them in reinforcement learning. That is, how one can leverage a model to better inform decision-making without having to interact with the world. We call this process planning with model experience. In this video, we will talk about one particular view of planning. By the end of this video, you will be able to explain how planning is used to improve policies and describe one-step tabular queue planning. Planning is a process which takes a model as input and produces an improved policy. One possible approach to planning is to first sample experience from the model. This is like imagining possible scenarios in the world based on your understanding of how the world works. This generated experience can then be used to perform updates to the value function as if these interactions actually occurred in the world. Behaving greedily with respect to these improved values results in improved policy. Recall that Q-learning uses experience from the environment and performs an update to improve a policy. In Q-planning, we use experience from the model and perform a similar update to improve a policy. Random sample one-step tabular Q-planning illustrates this idea. This approach assumes we have a sample model of the transition dynamics. It also assumes that we have a strategy for sampling relevant state-action pairs. One possible option is to sample states and actions uniformly. This algorithm first chooses a state-action pair at random from the set of all states and actions. It then queries the sample model with this state-action pair to produce a sample of the next state and reward. It then performs a Q-learning update on this model transition. Finally, it improves the policy by greedifying with respect to the updated action values. A key point is that this planning method only uses imagined or simulated experience. All of these updates can be done without behaving in the world or in parallel with the interaction loop. Imagine that actions can only be taken at specific time points, but learning updates can be executed relatively fast. This results in some waiting time from after the learning update and when the next action is taken. We can fill in this waiting time with planning updates. Imagine we have a robot that is standing near a cliff. Let's say its model knows about the outcome of stepping off of the cliff, but it is not accurately represented in its value function or policy. It can generate simulated experience of stepping off of the cliff and perform many planning steps on these transitions. Its value function will now better reflect that stepping off of the cliff is bad, and its policy will have it step away from the cliff. To summarize, we discussed how planning methods use simulated experience to improve policies, how random sample one-step tabular Q-planning uses a sample model to randomly generate experience, and how the value function is then improved using a Q-learning update.
So far, we've talked about two sources of experience, the environment and the model. In DirectRL, the agent learns from experience generated by interacting with the world, like in Q-learning. But the agent can also generate simulated experience from the model and use it for planning. Today, we will talk about one way to combine DirectRL and planning called Dyna. By the end of this video, you will be able to understand how simulated experience from the model differs from interacting with the environment. You will also understand how the Dyna architecture mixes DirectRL updates and planning updates. We've seen Q-learning, which performs updates using environment experience. Q-planning, on the other hand, performs updates using simulated experience from the model. We can combine these two ideas through the Dyna architecture. First, we will describe the main components of Dyna. We have the usual environment and policy. They generate a stream of experience. We use this experience to perform DirectRL updates. To do planning, we need a model. The model has to come from somewhere. The environment experience can be used to learn the model. This model will be used to generate model experience. In addition, we want to control how the model generates this simulated experience, what states the agent will plan from. We call this process search control. Planning updates are performed using the experience generated by the model. Let's look at a cartoon of how Dyna works. Here we have a simple maze and a robot trying to find its way out. It's a discounted problem. The robot receives a reward of +1 at the goal and 0 otherwise. As usual, the robot starts out knowing nothing. It randomly traverses the maze until it stumbles on the goal for the first time. Our robot only updates one action value, depicted in blue. This was the only transition that generated non-zero reward. This update is done by DirectRL. Dyna makes use of all the experience generated during the first episode to learn a model of the environment. The yellow states correspond to states visited during the first episode. The robot didn't visit all of them, but it visited most of them. Dyna performs planning on every time step. However, planning has no impact on the policy during the first episode. even though the model became more accurate in each time step. After the first episode completes, planning can really shine. In our cartoon, the thought bubble represents planning happening in the robot's mind. The grid world in the bubble represents the robot's model of the world. The yellow states represent where the model knows what will happen next. The model knows about all the states the robot visited during the first episode. Let's look what happens if we run the planning loop at the beginning of the second episode. Dinah can simulate transitions from any of the state action pairs the agent visited during the first episode. In this case, there are a lot of them. Planning replays these simulated transitions as if they happened in the real world. Each step of planning simply applies the Q-learning update to a simulated transition and updates the value function. With enough planning steps, the agent can approve the policy in all the states visited during the first episode. Here, planning produced a pretty good policy. The policy is not perfect. Can you see where it takes suboptimal actions? The policy is still random in states that were not visited before. We represent these states where the policy was not updated with white squares. Let's see how the planned policy works in the real world. The robot now knows how to get to the goal quickly after just one episode. In comparison, Q-learning will require many episodes to achieve similar performance. Dinah does more computation per step, but uses limited experience more efficiently. Remember, this is only a cartoon. Dinah would act slightly differently than shown here. The robot would continue exploring and planning on each step of the second episode. So the policy would take random actions once in a while, and the policy would continue to change and improve due to planning. We will discuss how to implement Dinah next time. In this video, we introduce the Dinah architecture, which uses DirectRL and planning updates to learn from both environment and model experience. That's all for this video. I hope you plan on coming back next time. We discussed how Dinah unifies planning, learning, and acting. This unification introduced some additional concepts like model learning and search control. Today we'll take a closer look at how all these pieces fit together. In this video, we will discuss a specific instance of the Dinah architecture called tabular DynQ. By the end of this video, you should be able to describe how tabular DynQ works. You will also be able to identify the DirectRL, planning, model learning, and search control parts of DynQ. Let's first discuss how tabular DynQ algorithm learns a model. Tabular DynQ assumes deterministic transitions. For example, when this rabbit chooses to move right in state A, there is only one outcome. The rabbit transitions to state B with a reward of 0. Likewise, if the rabbit moves right in state B, it stays in state B with a reward of 1. The left action in B always takes the rabbit to state A with a reward of 0. After the rabbit has experienced these transitions, the model knows what happens in these state action pairs. If a transition occurred once, it will always unfold that way in the future. The model can be certain about this. Let's look at the DynQ algorithm in detail. First, we have the usual agent-environment interaction loop. In the current state, the agent selects an action according to its epsilon greedy policy. It then observes the resulting reward and next state. It performs a Q-learning update with this transition, what we call DirectRL. If we were to stop here, we would get exactly the Q-learning algorithm. This is where things start to differ from model-free methods. DynQ will take this transition and perform a model learning step with it. To do so, the algorithm memorizes the next state and reward for the given state action pair. This works because we assume the environment is deterministic. DynQ then performs several steps of planning. Each planning step consists of 3 steps: search control, model query, and value update. In this algorithm, search control selects a previously visited state action pair at random. It must be a state action pair the agent has seen before. Otherwise, the model would not know what happens next. Given the state-action pair, we queried the model for the next state and reward. We have now generated a model transition. Finally, DynaQ performs a Q-learning update with this simulated transition. The planning step is repeated many times. The most important thing to remember is that DynaQ performs many planning updates for each environment transition. And that's tabular DynaQ, a simple instance of the Dyna architecture. Let's revisit our robot friend to better understand the DynaQ algorithm. Remember, this is just a cartoon to build intuition. Like before, it starts out knowing nothing about the environment. The robot gradually builds a model while interacting with the environment. The first episode takes 184 steps. In that time, the agent only changed the value of the state-action pair beside the goal. Without planning, the next few episodes would probably be just as long. Let's look at the next episode and study the impact of doing 100 steps of planning on every time step. The last time we talked about this robot, it was doing way more planning on each step. So this time around, it will take longer for DynaQ to find a good policy. After just one step, planning updated the values of 2 more states. Now the agent knows the correct actions in the final corridor. Let's run DynaQ a bit longer. The impact of planning is quite dramatic. DynaQ propagates the reward information across the entire state space. Eventually, the agent knows an effective policy for navigating to the goal from most states. The policy computed by planning only requires 18 steps to reach the goal, after just 2 episodes. That's more than 10 times shorter than the first episode. Tabular DynaQ performed many more updates to the value function than it would have without planning. DynaQ makes better use of its limited interaction with the environment. In this video, we learned how tabular DynaQ mixes planning, learning, and acting through the value function. We also studied how DynaQ updates its value function in a small grid world. We've discussed the Dyna architecture and how it combines planning, learning, and acting. We have also studied how DynaQ operates in a grid world. Let's get down to business and run some experiments to see how well DynaQ really works. In this video, you will use a small grid world to compare tabular DynaQ and model-free Q-learning. By the end of this video, you will be able to describe how learning from both real and model experience impacts performance. You will also be able to explain how a model allows the agent to learn from fewer interactions with the environment. Today, we'll run some experiments on this small maze environment. Like before, the agent has 4 actions. Transitioning into the goal state generates a reward of +1. All other transitions generate a reward of 0. This problem is episodic, and we will use a discount of 0.95. Let's compare DynaQ with different amounts of planning. We will compare 3 agents. Each one will use alpha equal to 0.1 and epsilon equal to 0.1. We initialize the action value estimates to 0 for all 3 agents. We ran the experiment for 50 episodes, 30 times, and then averaged the results. Let's have a look. We can plot the average number of steps the agent took to complete each episode after more and more episodes. If the agent is doing well, then the number of steps should decrease with more episodes. That is, lower on the y-axis is better. If we run DynaQ with 0 planning steps, we get exactly the Q-learning algorithm. As we can see, it slowly gets better, but plateaus at around 14 steps per episode. If we run DynaQ with 5 planning steps, it reaches the same performance as Q-learning, but much more quickly. DynaQ with 50 planning steps only takes about 3 episodes to find a good policy. DynaQ is far more sample efficient. Look at the y-axis. After 2 episodes, the policy found by Q-learning still requires hundreds of steps to escape the maze. For the same number of environment interactions, DynaQ can learn a lot more. This shows how planning makes better use of environment experience if the model is correct. Let's visualize what's going on in a slightly different maze. We use an arrow to show the greedy action according to the estimated value in each state. A state without an arrow means that every action is equally likely under the policy. After 1 episode, Q-learning updates just 1 action value, the one corresponding to the up action in the state next to the goal. This is the only state where a transition with the non-zero reward was experienced. It would take several more episodes to bootstrap this state's value back to other nearby states. Let's look more closely at how search control impacts planning. Our robot will do things slightly differently than DynaQ, but that's just to emphasize our point more clearly. We will start with 10 planning steps and call the planning loop 10 times in a row. So that's 100 steps of planning in total. As you can see, many of the planning updates fail to change the value function. In fact, the agent only updated the values of 2 state action pairs after 100 steps of planning. Let's keep going. This time, we will try 100 planning steps per call and let the agent run a bit longer. Even with the 100 planning steps, the first few calls update only a handful of action values. Why does the agent need so many planning steps to learn the value function and a reasonable policy? The agent needs many planning steps because search control samples state action pairs randomly. The planning update will not have any effect if the sampled state action pair produces a 0 TDR. This happened a lot in this environment because all the rewards are 0, and so are the initial values. What would happen if we ordered the state action pairs in a more efficient way? It turns out the agent could learn a good policy only using 1/6 of the planning updates. In large environments, random search control becomes even more problematic. If you want to learn more about this topic, check out section 8.4 of the textbook. In this video, we tested the tabular DynaQ algorithm in a simple grid world. We saw how planning can dramatically speed up learning. In our experiment, the more planning we did, the better the agent performed. Bye for now.
So far in the course, we've talked about how agents can improve their policies or value functions by planning with experience generated from a model. But what happens if the agent plans with experience from an inaccurate model? In this video, you will learn how to identify ways in which models can be inaccurate, explain the effects of planning with an inaccurate model, and describe how Dyna can plan successfully with an incomplete model. First, let's talk about what it means for a model to be inaccurate. Models are inaccurate when transitions they store are different from transitions that happen in the environment. At the beginning of learning, the agent hasn't tried most of the actions in almost all of the states. The transitions associated with trying those actions in those states are simply missing from the model. We call models with missing transitions incomplete models. The model could also be inaccurate if the environment changes. Taking an action in a state could result in a different next state and reward than what the agent observed before the change. We say the model is inaccurate because what actually happens is different from what the model says. So what happens when we plan with inaccurate models? The effect of planning with inaccurate models depends on how the model is inaccurate. In the beginning, the model is incomplete. Since the model can't produce a next state or reward, it can't be used for planning. However, as the agent interacts with the environment, the model stores more and more transitions. Then, the agent can perform updates by simulating transitions it's seen before. That means that as long as the agent has seen some transitions, it can plan with the model. Now let's think about how changes in the environment affect planning. Imagine that the agent has already visited every state action pair and stored its experience in the model. Then, the environment changes. A transition in the model no longer reflects the transition in the environment. What will happen when the agent tries to plan using its inaccurate model? If the agent tries to perform a planning update with one of the incorrect transitions in the model, the value function or policy that the agent updates might change in the wrong direction. Remember that planning improves the policy with respect to what the model thinks will happen rather than what will really happen in the environment. The model becomes outdated when the environment changes. Planning with that model will likely make the agent's policy worse with respect to the environment. Now that we've gone over the two main ways that models can be inaccurate, let's think about how agents could plan successfully with incomplete models. We've actually gone over one such algorithm already, DynaQ. Let's see how DynaQ does planning with an incomplete model. In the planning step, we must determine which state action pairs to query the model with. The model only knows the next state and reward from state action pairs it has already visited. Therefore, DynaQ can only do planning updates from previously visited state action pairs. DynaQ only plans with transitions it has already seen. So in the first few time steps of learning, DynaQ might do quite a few planning updates with the same transition. However, as DynaQ visits more state action pairs in the environment, its planning updates become more evenly distributed throughout the state action space. In this video, we talked about how models can be inaccurate if they are either incomplete or if the environment changes. Planning with an inaccurate model improves the policy or value function with respect to the model and not the environment. And DynaQ can plan with an incomplete model by only sampling state action pairs that have been previously visited. See you next time.
We previously talked about how agents can plan with models that are incomplete. Now, let's discuss how agents can plan with models that are inaccurate because of changes in the environment. By the end of this video, you'll be able to explain how model inaccuracies produce another exploration-exploitation trade-off, and describe how DynaQ addresses this trade-off. When the agent's model is inaccurate, planning will likely make the policy or value function worse with respect to the environment. That means the agent has a vested interest in making sure its model stays accurate. In this example, the robot's model initially says that the rabbit will go directly to the carrot if it chooses the move right. However, after moving right, the rabbit finds itself in the middle square. After experiencing this transition, the rabbit can update its model of the world. The update reflects that choosing the move right action in the leftmost square will result in moving to the middle square. We saw that the rabbit corrected its model after experiencing a transition in the environment. In general, an agent might want to double check that all its model's transitions are correct. However, double checking transitions with low valued actions will often lead to low reward. In changing environments, the agent's model might become inaccurate at any time, so the agent has to make a choice. Explore to make sure its model is accurate, or exploit the model to compute the optimal policy, assuming that the model is correct. When the environment changes, the model will be incorrect. It will remain incorrect until the agent revisits that part of the environment that changed and updates the model. This suggests that the agent should explore places it has not been to in a while. Let's think about how that might work. Roughly speaking, the model is more likely to be wrong in states the agent has not visited in a long time. For example, let's say the rabbit knows the turtle starts in the following cell. Since the turtle moves slowly, it can't move very far in the first few time steps. However, after a long time, the turtle might be in a totally different cell than it started in, making the rabbit's model incorrect. To encourage the agent to revisit states periodically, we can add a bonus to the reward used in planning. This bonus is simply kappa times the square root of tau, where r is the reward from the model, and tau is the amount of time it's been since the state action pair was last visited in the environment. Tau is not updated in the planning loop. That would not be a real visit. Kappa is a small constant that controls the influence of the bonus on the planning update. If kappa were 0, we would ignore the bonus completely. Adding this exploration bonus to the planning updates results in the DynaQ+ algorithm. By artificially increasing the rewards used in planning, we increase the value of state action pairs that haven't been visited recently. How exactly does this encourage exploration? Imagine a state action pair, SA, that has not been visited in a long time. That means the tau will be large. As tau grows, the bonus becomes bigger and bigger. Eventually, planning will change the policy to go directly to S due to the large bonus. When the agent finally visits state S, it might see a big reward, or it might be disappointed. Either way, the model will be updated to reflect the dynamics of the environment. Let's look at the shortcut maze to understand the difference between DynaQ and DynaQ+. In this example, the objective is to get to the goal from the start state as fast as possible. The rewards are 0 everywhere except for the terminal transition, which emits a reward of +1. The discount factor is less than 1 because we want to encourage the agent to reach the goal quickly. Both DynaQ and DynaQ+ use epsilon greedy action selection. For the first half of the experiment, DynaQ and DynaQ+ behave very similarly. In this case, the increased exploration by DynaQ+ helps it find a good policy more quickly. That is why DynaQ+ line is above the DynaQ line. Now, we create a shortcut on the right side of the wall. Let's see how DynaQ and DynaQ+ adapt to that change. Can they find the shorter path to the goal through the right side of the wall? Here are the results. DynaQ+ finds a shortcut soon after the environment changes. DynaQ, on the other hand, does not find the shortcut in the time allotted. Eventually, DynaQ will find the shortcut by re-exploring the entire state action space using epsilon greedy. However, doing so would require at least 7 exploratory actions in a row, so it could take a very long time. In this environment, the persistent and systematic exploration of DynaQ+ was key. In this video, we talked about how model accuracy produces a new variant of the exploration-exploitation trade-off. The agent has to explore to make sure its model is accurate. We also talked about how DynaQ+ uses exploration bonuses to explore the environment.
Hi, I'm Drew Bagnell. I'm the Chief Technology Officer at Aurora Innovation. I'm going to talk to you a little today about self-driving, robotics, and model-based reinforcement learning. You know, we're really in the beginning of a revolution in robotics, from manipulation to drones to self-driving. And these techniques are in general deeply dependent on machine learning. For instance, within the use of perception, we've had no credible story for how to do perception without machine learning for nearly 2 decades now. And what I'm showing in the video you're seeing is an autonomous vehicle, an Aurora autonomous vehicle, driving along in a scene of typical complexity for an urban environment. In blue, you're seeing a machine learning-based perception system detect and understand the motion of parked and moving vehicles. In gold, cyclists sharing the road, and in red, dense crowds of pedestrians. It's important in these applications to achieve extreme accuracy in all weather and occlusion. What's been interesting over the last, say, decade is the increase of importance of using machine learning in the decision-making process. Decision-making is very complex in urban environments. I'm showing here, for instance, an autonomous vehicle finding a gap in a dense flow of pedestrians. What makes this difficult is the importance of context and other actors in the scene. And it turns out to be very difficult to build and hand-tune rules for problems like the one being demonstrated here, or even things as simple as a stop sign or a merge. And you'll note in these examples that I'm talking about in robotics that they all rely on continuous states and actions. I'm showing here a spectacular example of model-based reinforcement learning applied to acrobatic autonomous helicopter control. In this work by Peter Avila and his colleagues, they demonstrated they could use model-based reinforcement learning techniques on the continuous states and actions, the positions, velocities, and controls of a model helicopter and make it perform exceptional acrobatics. The key to making such techniques practical is the use of continuous state and action models of the helicopter dynamics. So models, what do I mean by models? By a model, I mean a transition function or dynamics, a function that maps the current state and action to the next state, as well as a function that can evaluate the cost at a particular state and action. A dirty secret in the field is that practically all robot learning problems that involve decisions are in some way model-based. And you might ask, why is this true? Well, fundamentally, interactions between, for instance, robots in the world are expensive and time-consuming. And it's often said that it's, say, better to die in simulation than it is in the real world. The way to formalize this intuition is to talk about sample complexity. How many interactions with the world are required to achieve high performance? And what we've learned, both practically and very recently theoretically, is it can take exponentially fewer interactions to learn with a model than it does to learn without. Okay, what I'm going to take you through now is how we take advantage of a continuous state and action model using quadratic value function approximation. Quadratic value function approximation is a powerful technique for model-based reinforcement learning that goes back to optimal control in the 1960s. This class of techniques was the one used in the spectacular helicopter acrobatics you saw above, and it's widely used in creating trajectories from drones to medical robots to manipulators to self-driving vehicles. And this quadratic form approximation of a value function, again continuous in state and actions, is particularly elegant for a few reasons. One, for a simple class of systems, notably ones whose dynamics are linear and costs are quadratic, this value function, quadratic value function approximation is exact. It's not an approximation. For other problems where the action value function is convex or locally convex and the continuous states are actions, it turns out to be an excellent local approximation of the true action value function. And the key here is that given this approximation, we can rapidly compute the optimal policy in closed form, even with continuous actions. Okay, so it's an interesting exercise to go through and actually try to compute what the optimal policy is. It's worth doing this by hand for a single scalar variable x and state, and for a single scalar control or action A. If you're familiar with matrix calculus, this is a very quick computation, but if you're not, it's worth struggling for a while to understand how it works. The nice part is, once you compute this optimal policy, you can plug it back in to the action value function and extract the optimal value function v, and it'll turn out to be quadratic as well. The general family of techniques that take advantage of this are known as differential dynamic programming. Once you have gone through the exercise we described above, you can pull it together with the techniques you've already learned in dynamic programming or in using the Bellman equation and compute an optimal policy for all time steps. And the idea is we go backwards in time in the standard dynamic programming form. We compute at every time step a series, particularly a Taylor series approximation of the model and the known cost function up to first or second order. And then we use the Bellman equation to back up a quadratic approximation of the action value function, given a quadratic approximation of the future value and the quadratic approximations we just computed of model and cost. Then you use the exercise we did above to compute the optimal policy and thus the optimal value at time step t-1. And this gets iterated backwards in time. Now it's very common, and in fact used in the approach we described above, to then go back and refine the Taylor series approximation by taking advantage of the new policy we have. Think about this as giving us a new point to linearize the model about. Okay, there's lots of details to both the algebra and to getting this to work. And fortunately, there's lots of great resources online that you can take advantage of to learn more about these techniques. Here you can find my notes on the techniques I applied that we discussed above, as well as Katerina Fragadaki's lectures on the same. I'll also note that Yuval Tassa's paper on online trajectory optimization is particularly clear and easy to work through for this approach that I just described. Okay, now that we have a technique that can take advantage of a continuous state and action model and learn a policy which may be optimal or near optimal, we'll discuss next how to build models so we can solve RL problems. Thank you for your attention.
Congratulations, you've just finished Module 4, where we learned about planning, learning, and acting. Let's go over the concepts and algorithms we've covered in this module. In Lesson 1, we introduced models and talked about the difference between distribution and sample models. Distribution models store the probability of every possible outcome. However, this may require a large amount of memory. Sample models are usually much more compact than distribution models because they don't explicitly store the probability of each outcome. In Lesson 2, we introduced one-step Q planning. Q planning uses the same update as Q learning. However, it uses experience generated by a model instead of real experience. In Lesson 3, we introduced the DINA architecture. DINA incorporates both planning and learning in a single agent. We saw that a DynaQ agent can learn much more quickly by using many planning updates. Models aren't always accurate. In Lesson 4, we talked about how inaccurate models affect planning. We pointed out how DynaQ can plan effectively using an incomplete model, but not if the model is wrong. Finally, we introduced DynaQ+. This algorithm uses a reward bonus in its planning updates to encourage exploration. By exploring, DynaQ+ keeps its model up to date and accurate, resulting in better performance. We covered a lot of material in this module, so well done keeping up. You've made it through the whole course on sample-based learning methods. Let's quickly review what we've covered. We talked about two approaches to learning from sampled experience. The first was Monte Carlo, which averages returns to estimate the value function. The second was TD learning, which uses the estimated next state value in its target. We saw that TD learns from sampled experience like Monte Carlo, but also bootstraps like dynamic programming. We showed you how to implement the TD algorithm to estimate both state value and action value functions. We then talked about control using SARSA, expected SARSA, and Q learning. SARSA is an on-policy algorithm. It estimates the value of the policy it is following. Q learning is off-policy. It estimates the value function for the optimal policy. Expected SARSA can be used on or off policy. It explicitly calculates the expected next state value in its update target. This expectation can be conditioned on any policy, so expected SARSA can be used off policy. We showed that Q learning is a special case of expected SARSA. In the last module, we talked about planning with model experience. We introduced the DINA architecture that incorporates both planning from model experience and learning from environment experience. We discussed DynaQ, which combines Q learning and Q planning. In an experiment, we saw that DynaQ's planning updates make it more sample efficient than Q learning. Finally, we considered what happens when the model is inaccurate. We showed you how DynaQ+ adds an exploration bonus in the planning update to encourage exploration. This bonus helps DynaQ+ notice changes in the environment that DynaQ would not. We hope you've enjoyed learning about sample-based learning methods. In the next course, we'll see how to combine sample-based learning with function approximation. We will learn about generalization, a powerful tool to scale up reinforcement learning and dramatically improve sample efficiency. Many of the concepts you've learned will transfer, but there will be a few new challenges. Stick around to find out how we resolve them.